right, just waiting for things to go live. And all right, looks like we're live. All right, so thanks for tuning in for another stream today. So to recap what we've been doing so far, we've been building this ROS2. We've been building this robot chassis with the hopes of doing a ROS2 based differential drive, like LiDAR navigating SLAM robot. So in the last couple of streams, we went over the hardware and we did some hardware overview, some experimentation, and in the last two streams, we soldered all of the logic boards together, or the main logic board together. We also showed that we can in fact run a Raspberry Pi off of the Pi Pico by backfeeding power through the VBus pin. And so we basically were at, since the last stream, I cleaned up some of the old like double-sided tape that was stuck to the chassis, gave it a little bit of a freshen up. So basically where we're at right now is effectively just a little remote control robot. We've been using a Pi 2W or a Pico 2W. We've been using some software that we hacked together, stole, repurposed, whatever, from the balancer robot that we did on stream a couple of months ago. But today what the goal is to do all of the 3D modeling that we need to do to hold components to the robot. And so what that's mostly going to amount to is, as you can maybe see, there are a bunch of mounting holes already on the robot, on the robot frame that the manufacturer of this chassis had put in. And so there's probably two main sets that we need to be thinking about. So there are these four non-countersunk holes that are actually a 100 millimeter vase mount standard, and then there are four countersunk mounting holes that are for a motor control board that this company used to make, but obviously they no longer exist and we're not using one of those. I think it was called the serializer, if anybody remembers. But again, we're gonna have to build our own mounting jig, and we've done our own logic board, as you can see down there. But today we're going to be repurposing these mounting holes and making some 3D printed components that will allow us to mount the hardware we need on here. And so to start off with, I think the first thing that we should probably look at is the battery mount. Because if you recall maybe seeing in the last couple of streams, I had literally taped with electrical tape the battery to the top of the robot frame, which is obviously not what we want to be doing. So we'll start off by first making the mounting bracket that'll hold the battery under the robot frame. And so let me switch to my phone camera just so that you can kind of give an idea of placement. And so let me flip on DroidCam here. And we shall, unfortunately the arm's over there, so I'm going to be holding the camera. But so let's flip over to this camera here. All right. So as we can see, here's the frame. I'm thinking that what we'll do is from that relay bot video I did back in May. I had actually stuck a piece of Velcro, adhesive Velcro strip to the battery. So what we'll do is we're going to build a bracket very similar to what we did in that video, where essentially it just bolts to the battery's just going to be held on with Velcro. But we just need to build the mounting bracket because I don't really want to put the Velcro adhesive onto the frame itself, just because it'd be a pain in the butt to get off if we ever want to change things. So we're going to start off with, so I'm thinking that, let's figure out a good position for this inside. We'll be able to do it later, or move things around a little bit later, just because of, hold on. Let me switch back to here so I can move some stuff, have my hands free anyway. So we'll just pull that down here, do the tape, not break the tape. All right, let's see here. Right, all right, so now that we got that, I'm thinking we can probably get this out of the way. Probably stick the battery in something like this. So we'll probably stick the battery in somewhere like here. And so we can see that, you know, like the battery's mounting position is probably going to be, you know, not that much further back than the forward two mounting holes. And because these four here are that what was originally intended to hold electronics under the frame. So we're going to start off by doing some measurements to figure out how far apart these holes are. And then we're going to make the little bracket. And then after that, we'll flip it over and make the bracket that holds the Raspberry Pi and the LiDAR. And maybe the camera. Because we did put that servo header in here in order to be able to drive a tilt servo for a camera. So let's switch back to the desktop here. All right. So let's start with opening up FreeCAD. FreeCAD. Oh, I lost my icon for it. Okay, anyway, FreeCAD. And then what we're going to do is we did have this bracket that we made last time that holds on the logic board frame in the bottom of the holds it to the bottom of the chassis. So what we're actually going to do is I forgot that there was another project that I had made. I think I just called it Stinger. But these are actually this is the model for those adapter plates that you saw when I what do you call it? When we swapped the high speed, the 600 RPM motors out for the 200 RPM motors in the chassis. This is actually the bracket that I made. So I do have a 3D model of this still. So actually, we're going to use this project to actually make all the mounting hardware. And then we'll merge in that other bracket into here. You know, let's see if we can actually just move it. Hey, look at that. Cool. Clear. Perfect. So now we'll close this document. Interesting. So if we close PicoPiBot, save Stinger, what happens if we reopen Stinger now? Open recent Stinger. Perfect, no errors. I love it. All right, so that was easy. Perfect. So we'll hide all that, and then we're going to start by creating a new part for this is going to be our battery holder. Battery holder, and then we need a body, a battery holder body. All right. So we're going to start with a simple sketch. We'll start with the XY plane. All right. So, oops, that's not what I want to do. So, front. What did I do? Hold on. I may have done not what I wanted to do. All right. So actually, let's rotate our cube into the normal viewing angle with here. Okay. So sketch. It's going to create so we'll do XY plane, and yeah, there we go. All right. So to start off with, let's take some measurements. So we're going to flip the robot over. I really wish I moved the arm over here, but just to start off with, what we're going to do is what I'll do just to try to ease things up is I'll set the caliper up to like measure the dimension, and then I'll point the phone camera at it so y'all can see what I'm doing. So we've got and before we do that, let's decide on how large we want. What artillery complement will the robot have? Nerf cannons? No. We're gonna hopefully laser pointers to make the cats chase it around. I don't know. So the front pair of. All right. So let me set up the calipers here. So the front pair of holes is. It looks like. Oh, I'm measuring the wrong ones, of course. I was like, wow, 100 millimeters, that doesn't seem right. That's the vase amount. So what we got here looks like 73.5 on the front two. And just so y'all can see, let me wake the phone back up, desk cam. So it looks like these two holes are, it looks a little more correct from my perspective, but looks like these are 74. So we can see that this one's centered. We can see that this one is centered if I'm actually looking at it top down. So it's 73.5 millimeters between those two. So let's, oops, let me go back to the desktop. So we're going to define rear, top, rear, so this is front. Okay, so we're going to, the front is down here. So these two are the front holes. So we're just going to define 2 points here. And just to start off with, we're going to make these symmetric across the axis here. And we said these are 73.5 millimeters apart, 73.5. All right. And then let's look at how far away the, or how much spacing is between the front and the rear set of holes. And that's looking like, this one's actually harder because these are actually kind of off canter just a little bit. So it's looking like 86 millimeters. So it's kind of hard to tell just because these holes are quite spaced. So I'm trying to, or what I'm trying to do is show. So as you can see, these are just about lined up, and this one's on here. But the holes on the back are further apart than the ones on the front. So we can see it's just about 86 millimeters spacing. So let's define a point up here, or define 2 more points up here. And these are also, we're going to assume that they're symmetric for now. So these are, we'll define as symmetric around the axis, and the distance is, we said 86 millimeters. And we know these are going to be further apart. So let's measure the distance between these two rear ones. Oh, it's almost square. Looks to be, I mean, you know, really hard to visualize half a millimeter, you know. So if we put that there, I put that there. It's also entirely possible that this thing was designed with imperial units, or U.S. customary units instead of metric. So it's actually more looking like 79.5 for the back two spacing. So we'll define that as 79.5. All right, and we'll also just define this as, actually, sorry, we'll define this as symmetric as well. Oh, I've over-constrained this drawing. What have I over-constrained? Remove one of these constraints. Oh, because it can't be made symmetric across the... Okay, anyway, 86. Actually, so what we've got going here is if we define this as, so half of 86 would be 43. Oops, would be 43. So what we'll do is we'll define, this is going to be 43, and these are going to be symmetric about the x-axis here. No, we're still over constrained. How? Okay. Okay, whatever. We'll just leave it as it was before. Define this as 43. Perfect. And now we've got our little points that we know where to cut our holes. So what we're going to do now is define basically holes around this that are where the threaded inserts are going to mount. And so we're going to use M3 bolts to mount this. So those are 5 millimeters in diameter. So we'll just define some holes here, or well, some circles, and we'll make them holes later. So here, we'll do that. We'll do that. We're going to define an equals relationship. So these are all now 5 millimeters, and then I'm thinking we'll make this look like little ears, you know. So if we look at the battery, how long is this Velcro strip? The Velcro strip is, oh, look at that, 100 millimeters long, 10 centimeters. Very standard measurement. All right, so turn that off. So what we're gonna do, all right, so, what to do? So we got these holes, we've got 5 millimeters, we're gonna define our inner shape here. That will be just a centered rectangle. We want this to be 100 millimeters wide. Oh wow, I almost got it perfect. 100 millimeters on one axis. And we'll define it as, well, whatever this is on the other axis. So we'll define this as like 75. All right. That's not like pinching anything under here, right? All right, so how we're going to make this is, and I might have got a little ahead of myself here. Okay, so what we'll do, wow, okay, I did get ahead of myself. All right, we'll do an arc, and we'll do this, this, we're gonna, oh, oops. Ah, no, hey, that's fine. And then we're gonna do this. These are all going to be horizontally aligned with each other. Doop. Those are all horizontal. These are all horizontally aligned with each other. The radius here is going to be 7.5 or 7 millimeters. That'll give a 2 millimeter wall around the threaded insert. Actually, you know what? We'll only give it a 1.5 millimeter or 1.6 millimeter wall, so we'll do 6.6. And we're gonna make these all equal. They're all going to be equal. Can't do equivalencies between them. Okay, that's fine. 6.6. 6 and 6.6. All right. So we shall then. What's the spacing here, though? 5.5. Okie doke. How wide is our battery? That's a good question, too. 43. Also, the real question is just how forward this thing is mounted. We go back to our mock-up here. Oh, it'll be mounted further back. Okay, and actually, the battery is going to be mounted on the backside, so that's fine. We can, these can be whatever we want anyway. All right, so we now need to do some outer linkage on this, and I think how we'll handle this is we'll just connect these like this. We'll connect those that way, we'll connect these, figure out what this spacing is. I think it's 5.5 millimeter. Yeah. So We're then going to come over here, do that, come up, come over. Oops, that's horizontal. There's going to be 5.5 millimeter spacing just to make things symmetrical, because symmetry is nice. All right. All right. All right. 5.5. Perfect. You don't need symmetry, but symmetry just looks visually appealing, right? And actually, we don't want this inner rectangle. We actually don't want this inner rectangle. We don't want a hole here. This is our table base, essentially. Okay. Well, actually, 75 mil, 75 mil. Okay, so we've now made this all decidedly unhappy. All right, but let's remember our dimension was 100 million. We'll do a draft square here. So this will be our 100 mil. This will be our 75 millimeter. This will be, oh, we've already defined that. So this is 5.5. And these are also 5.5. Okay, cool. The draft is just, it helps you do drawing. It doesn't actually come out as part of the border of the shape. So what we'll do now is we'll define a pad of 4 millimeters. This will form the base of our battery mount. And then underneath, so this is the top. And the top is actually where we're going to bring out the posts for mounting this. So what we're now going to do is we're going to apply a sketch to the top. And we're going to import all of these circles here. Doop, 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 and doop. Okay. So we're going to restore our hole, the hole drills here. So that's that. That's that one. And actually what we can do as well is do that and that. There we go. Do that. We'll do this one. Oops. Why did that not work? This. Coincident. Okay. That, coincident. Or not. Okay. Something's not happy there. We'll have to figure that out. So we'll do that. We'll do that. That's also auto constraints cause redundancy. Ugh. Okay. I don't know why that's not wanting to link up. We'll do that one. We'll do this one. Make these points basically what we're doing here is we're reassigning the center here. We're then selecting this outer circle and the circle we're drawing, hitting C for, come on. Sorry, we're selecting a point on the outer circle and then C to make these coincident, which means this circle line has to go through that point. But up here, these inner circles are not wanting to be coincident with the inner, and that's annoying. So we're going to retry the import. So GX, re-import that, centered circle, make these coincident. Nope. What is going on? You know what? Fine. Oop. Okay. Interesting. Let me make sure these other circles are actually put in the right spots. Okay. So what we're going to do is we're just going to do equivalencies. So we'll put the center there, put the center there. Oops. All right, undo equal. We're going to select that circle, and this circle. And we're just going to assign an equivalency. Cool. And then why? Hold on. This one is not thrilled with its existence. Oh, because the centering didn't work. There we go. Now we're all constrained. All right, so then we're going to do another pad of, this time 3 millimeters. That'll give us 3mm to route a wire or anything under here if we so choose to. Let me just, what does 100mm look like under here anyway? Will it even fit? That's a good question. So we set this at 100mm. Yes, 100mm will fit just fine under here. All right. And yeah, given ourselves the 3mm spacing to allow routing a cable, there's something underneath. So that is our first part, and just to make things a little nicer, we'll round these corners off because 3D printers can't actually print perfectly 90-degree corner, or well, they can sort of kind of print 90-degree. They can do outer 90-degree corners, they can't do inner 90-degree corners, but that's fine. We'll do some good old rounding, give it a 3mm. I think it's called filleting. Yeah, fillet. And this is our battery plate. So let's actually rename this to battery plate, just so we know. Battery plate body. All right, we'll export this. Bring it to STL. Make a new folder called Stinger. Stinger battery plate. Save. And then we're going to bring up our slicer for our printer. And then we're going to go to our 3D printing stuff. We're going to put our other Stinger motor stuff into the Stinger folder. All right. Stinger, rename this to motor plate. All right, so preview, we're gonna do a new project here. I'm gonna bring battery plate in. It's gonna be printed vertically like this. We're gonna use blue PLA to print this because I'm thinking that, a good color complement is orange and blue, right? Obviously black goes with just about anything, but just we'll make it out of blue PLA because that's one of the filaments I actually have loaded in the printer. But we'll subtract that. We will do our setup, our standard setup. We'll do 3 wall loops for strength. We'll do our gyroid infill just for, okay, so generic PLA. All the standard options is going to take 44 minutes to print. So that'll give us some time to work through the next couple of components that we're printing. All right, so it'll take 21 grams, 26.77 grams. Where did I get 21 from? What was I looking at? I don't even know. So print that. Go to the printer. It's going to take 50 minutes. Send. All right. Perfect. So now that is printing, we can look at how we're mounting the LiDAR, which is going to be the most complicated component of this whole dang thing. So let me go grab the LiDAR just so we can start measuring things. And somebody's probably already looked up the hole pattern on these LiDARs, but we're gonna, just so we can, learn, right? We're gonna measure it ourselves. All right, so you know what? Before I do that, I'm gonna have to take out the bolts on this. So let me grab my Allen wrenches. And so we don't necessarily need the LiDAR immediately, but let's mock up what it's the layout of the part. Again, hold on. I need a Raspberry Pi. Hold on. This is the one I'm going to use. Or actually, I think this is the one I'm going to use. Do I use a 4 gig or an 8 gig Pi for this project? How much compute do I think I'm actually going to need, or data? Well, it's going to be mapping stuff. So, or actually, I want to use my other 8 gig in my big robot. So let's grab the 4 gig Pi. So let me grab the 4 gig Pi. Let me grab a camera. And put this pie back over here. And alrighty. So, I'm gonna turn the camera back on. Alright. Wow, that didn't work. Alright. So we got our handy dandy 4 gig Pi. I think it's a 4 gig Pi 4 gig. Doesn't really matter. So let me turn on my phone camera again. All right, desk cam. So I'm thinking that the layout for this stuff is what we'll do is we're gonna put the Raspberry Pi probably just up with the ports just in front of this the caster screws, and then we'll try to put the LiDAR a bit forward mounted. We're going to try to center the cam at least horizontally, correct anyway. And remember these hole spacings are not even, so we're going to have to measure, where the center of the LiDAR is relative to the mounting hardware. But I'm thinking that this gives us, and maybe we don't do the tilt servo immediately. I mean, we'll put in some mounting holes so that we can actually mount the bracket if we get around to it. But I'm thinking that our best bet probably is to mount the Pi back here. Maybe, maybe we actually mount it a bit further back. The thing is, the mounting holes are here, unless we build little ears that come off and hook into these back too. Because these aren't actually holding up anything in the back. There was meant to be a little button panel that screwed in here, but I never bought it. And now that this company's out of business, it's never coming back. But, Interesting. Okay. Sorry, I lost OBS. There we go. Okay. So, what do we do? How does this work? Maybe we align these so that it looks kind of like that. I don't know. It's not like I'm taking the caster off while the thing's operating. And we do want to mount the LiDAR as low as possible. So actually, let me pull the camera out of its box just so we can kind of see where it'll line up. Fresh Pi cam, eh? It's nice that these days they include the other cable that you need for the Pi 0 and the Pi 5. Let's pull the cable out of it. Or actually, maybe we leave the cable into it just so we can measure how much we gotta flex it. Hold on. Immediately goes down this access hole here. All right. Yeah, the funny thing, here, right, is let me turn on the phone camera again. Is that with the cable bend that we need to do on the camera, it's not, it's not that much lower than where the LiDAR is mounted currently. And I thought I wanted to mount the LiDAR lower because, if we can see right now, it's pretty far up off the frame. But, if we, or maybe what we do is we mount the camera a little bit out front further so that it can be mounted lower, right? Because we really what we're working with here is the bend on the cable. Because I've always, okay. Anyway, let's see. What am I thinking here? So, if anything, we'll mount the camera a little forward. It doesn't have to be flush with the frame. We can mount it a little forward to give us some margin on the robot. So what we'll do is we're gonna assume that the leg of the LiDAR will mount in line with this front mounting hole, and then we'll mount the Pi just to give it some clearance anyway. We'll mount back here. I don't think I actually want to. I'm still trying to decide whether I want to mount the thing up high enough such that the connectors go over. And actually, this probably isn't that tall. So if we have to do the 5mm to mount the threaded inserts up here, that might actually just cover this. Let me check that real quick. Calipers. How far do these come up off the frame here? Yeah. It might actually just be 5mm. Let me grab one of my threaded inserts because that'll be a good metric here. Basically, the little threaded inserts that we actually use to make threaded holes on the 3D print. Actually, yeah, it's taller than the post coming out of the stand, the caster. So yeah, we don't even need to worry about this this back section here. Okay. All right. Let's start with modeling the plate. Anyway. So overall, what we're going to need is just enough. Okay, hold on. It's inglorious. So we're going to need a plate long enough to extend the calipers to their maximum length here. Not their intended purpose. Oh, I can't. It's too long for me to measure. Okay, what we're going to do, we're going to assume, or I should say, we know that the pi, we know how far apart these two holes are. So if I measure everything back here relative to this hole, we actually know how far apart things are. So let me put the thing back down. All right. So what we at the very least, what we'll start with is the mounting hardware for the LiDAR, right? And I've not got this particularly center, and I probably won't ever. So what we'll do is trying to think of something a little aesthetic. Maybe do we try to map, come up with something that meshes with the triangle that this frame is. So let's. I don't know what the dimensions of this triangle are anyway, but we'll draw this as a triangle as well, just to try to mesh with visually with this thing. It actually might even work. Sorry. All right, so we'll define it as a square up front, and then we'll define it as because essentially what we want to do, we want to build this as like a fully enclosed thing, just because I now have I now have the two kittens, right, and they currently are still too young to understand don't chomp on cables. So if I want to leave a robot on the floor, it can't have any cables little cables exposed. So we have a reason for making sure that everything is enclosed. Yeah. Okay, so yeah, let's start off by defining the plate. And the best way we can go about doing that is we'll assume that the walls, actually, let's pull FreeCAD again here. Let me move this stuff out of my way so I can use my arms. Actually, access my limbs. Access my limbs. Okay, so we'll do the plate and we'll hide that, and we're now going to make the part for the top plate. Rename top plate. Actually, let's do the component plate. Or, well, top plate. Why not? Top plate. Rename top plate body. Do a sketch. Put that on the XY plane like we've been doing. Do top here. Oops. Like sketch, sorry. Alright. So this is the front. And so we need to draw our... What we'll do is we're going to define this be... Again, we're going to use our 5 mil. Well, actually, we'll just make it all equal. So we need to do... Sorry. What we need to do here is... Because we got a 100 millimeter square mounting system, because it's... Or I should say, the reason the robot has a 100 millimeter VESA mount, like, the reason the holes are there is that the plan for these robots was to mount little mini PCs to that. Or, well, in 2008, or 7, when this frame came out, the goal was to mount little mini PCs to them. And the company, it was this, I think this brand called iCop, if I recall correctly. They were these, it's about the form factor of a modern NUC, but I think they were like 1 gigahertz 486 compatible, like maybe. I think there may have been some 586 instructions. I remember that you were supposed to run Windows CE on it. It couldn't run XP, if I recall. You had to run CE. It was that they were real big on trying to make everybody adopt Microsoft Robotics Development Kit, Microsoft Robotics Framework. I can't remember the actual names of the product. Or Robotics Framework, Robotics Studio. I don't remember what it was actually called, or or hold on. Unmute myself there, so you'll want to hear that. So we'll start by I already made them all equal. Okay. So now we'll define these as symmetric across all of the axes. There we go. Right. Alrighty, so we've got our rectangle. So now all we need to do is define a distance of 50 millimeters, because it's square, and then these will be 100. These will be 100 millimeter apart, right? 72. No. Yeah. And 100. And 100. All right, cool. So we've got our base mounting hardware, and we're going to do a centered square. Actually, we don't want to do the centered square, because we want to do our tapering off, because we've got section back here that we have to make to hold the Raspberry Pi, because this is just that front centered bit. So we'll define 3 sides, right? All right. And so these will be 5 millimeters, I think. We'll call it. I think that might be over-constrained because, oh right, these aren't symmetric around the axis. So we'll make them that way. So 1, 2, 3. Symmetric. It doesn't work. Actually, we can just do 1, 2, 3. Symmetric. There we go. Now we don't need to define we only have to define the split there. That'll be 5 millimeters. We can also check on our 3D print. Nice. There we go. It's printing. All right. So, and those really at this point we're just trying to figure out. These are going to be horizontal of each other. We just have to figure out how far back we want them to be. What we'll do, we'll just make these horizontal with that as well, right? Then we're going to taper it back to whatever we need to mount the Pi. Although maybe I don't want to do a triangular themed tail section, just because we might want to be able to access the ports on the Raspberry Pi. That would probably be a good thing. So never mind on that. There's also conceptually the way that if we mount the Pi this way, there's going to be no way we can get the dang SD card out of it unless we take the Pi off. Decisions. Oh well, rip the triangle idea. So we'll say this is 5 millimeters, and then bring them in. Try to figure out how far in we want them to go. And so, actually, we can figure out exactly. So let's bring the Raspberry Pi. Let's bring this back over here. So we can tell how far back we want them to go. If we decide where the tail end of the Pi is, we've got the LiDAR still stacked up here. What do we want to do? Do you want to think? Because we do want, we don't necessarily want the Pi out this far, because basically, the mounting holes are here. The end of the Pi is another, 50 odd, 100 odd millimeters out here, and then this will be a little flappy if it doesn't have a way to anchor. But it's also, kind of onerous. I don't know how I feel about this. Because I don't want to put too much, what do you call it? Plastic down, because I do like seeing the orange of the frame, right? It's a very pretty orange. So we could, whatever. I don't care. We can always redesign it later. PLA's cheap. So what we'll do next is we'll figure out how long we want the tail section of the. We'll assume that our Pi is aligned with, we're going to assume that our LiDAR is aligned with, let me go back to my phone camera here. We're going to assume that the LiDAR's front section is aligned with the first mounting hole, and then what we'll do is we'll assume that the Pi is, maybe we can say that's like 5 millimeters or 10 millimeters. It's probably like 10 millimeters. Yeah, we'll say that the Pi mounting hole is then 10 millimeters further back. From the other mounting hole. And then we'll drag some little mounting tabs, some locking tabs that come out, but we'll make them, we'll make them like, actually, no, I don't even know if I want to make those little tabs. We might as well just. And the reason that the Pi wants to sit, or we're going to sit the Pi back here, we want to do it that way. Nah. The reason that we do want to set the Pi back a little bit is that we do want to give ourselves the option of adding like the AI hat or something later, so we need to give it some vertical clearance. But yes. How about we could also say that the back of the Pi is aligned with. Actually, just a... We could say that the Pi's front two mounting holes are going to be aligned with these back two mounting holes here. So yeah, I think that'll give us the clearance that we need. Maybe. No, probably not, actually. So yeah, actually what we'll do, we'll just define this as 1 centimeter back from... yeah, what we'll do is we'll define the Pi's mounting hole here as 1 centimeter back from this mounting hole here, and then it'll come out just however far it needs to be. So let's switch back over to the FreeCAD. Okay, so put this over here. All right, and so now, okay, that whole thing was to say that we want to know how far back the frame needs to go, and that's going to be, we'll just decide here. We'll say it's basically going to be it's effectively 74 millimeters, or something like that. Realistically, this ought to be defined by some dimensions of the Pi. So actually, what we'll do is to make things easier on us is just to start getting some of this mounting confusion out of the way here. Let's actually pull up the Pi 5 hole spacing guide. So we got RPI 5 mechanical drawing. Here we go. Raspberry Pi 5 mechanical drawing. Okay, cool. So the holes are 49 millimeters apart. They're inset by 3.5 millimeters. So that's what we can do. Perfect. So we're going to define I believe the Raspberry Pi uses M2.5 mounting bolts. So that's the threaded inserts for them are 4 millimeters. So we'll define this as inset by 1 centimeter or 10 millimeters. And then these are symmetric of each other. So we'll just define these as equal. Can I hit E or something? Yeah, constraint equal. And then these are mounted symmetrically across the center. They are 49 millimeters apart from each other. Alright, and then let's define the other mounting holes for the Raspberry Pi. So that shall be... Actually, the Pi 5 is a lot friendlier than... Or actually, sorry, the Pi 5 is actually friendlier than the mounting holes. At least they're a rectangle. I was trying to do something for the Arduino the other day, and they have square. I think they have... Or was it the Arduino that I was trying to mount? Something I was trying to mount recently. I do think it was an Arduino. They have offset holes. Really annoying. There's a Pi 4. I can't freaking remember. Okay. So we're going to do 2 more up here. This will be defined as... These are all equals 2 as well. I think, what is it? Let me just check. RPI 5 bolt size. I think it's M2.5. M2.5, yeah. Oh, I could have checked by just looking at the diameter of the drill. Yeah, 2.7 mil drill. That's an M2.5 bolt. So these are in fact vertical of each other. That is really good. That is really good. So they are 58 millimeters spaced. And these are going to be symmetric across the central axes. Straight symmetric. These are vertical. Perfect. Okay. And then these mounting holes to the edge of the board are... It's going to be... Okay, well... That's going to be 50... It's going to be 85 minus 58 minus 3.5. So we'll define... And so that'll be that's the inner wall. That's before we define. That's, again, this is also going to be, we start defining walls. So we'll define our walls as, I always define them as like 3 millimeters thick, I think. Let me actually check one of my other designs here related to a Raspberry Pi. I'll open, I think I put this in mobile manipulator. Mobile manipulator, hold on. Or Lake Kiwi parts, right? Yeah, that's what I called it. Camera mount, oh yeah, my little, it's a different project, don't worry about it too much. Pi case base, right? That's what I called this, right. Alright, so how thick did I make this exterior wall? It might be 4 millimeters. Why did it not let me measure? There we go. 2 millimeters I did. That's a little thin for PLA. So we'll do 3. We'll assume walls of 3 millimeters, just so they're not too fragile. So if we do quick old Python, so we got 85 minus 58 plus 3.5. And that gives us 23.5 millimeters to the edge, and then plus 3, so it'll be 26.5 to some kind of outer wall. And so let's define that. So we said 26.5 to some outer wall. We'll constrain these points to be symmetric around the axes. Symmetric. And again, we said the inset here is, because these are circular, the inset's also going to be, 3.5 millimeters on all sides. So we can define our vertical walls here. And these are going to connect up to this. Make sure that these are horizontal. Do that, do that, do that, do that. This gives our little outer shape here. And we can define a spacing from the center of this drill. We're going to do 3.5 will get us to the outside, plus another 3 for our wall, right? So that's a total of 6.5 millimeters. Right, alright, cool. So total of 6.5 millimeters, and if we're coming off of... and how to do our cutouts here. So, oops. We'll do that in a second. Oh, fuck. Drop the liner. That's not good. Okay. We also need to make some cutouts for components. Here, sorry. Let me go back to the desk cam. We need to do some cutouts for components like, this central insert here and these screw mounts, because we might actually want to, connect something there. These are going to be countersunk, so we don't have to worry about these. But we do need to do a cutout for this central cable channel here, and then we'll need to do a cutout for this section. So this is basically just, an ellipse cut in, this is centered, and just to prove that, this should be 50 millimeters between the center and so should be it's basically 50 millimeters. It's a channel that's 18 millimeters on one axis, and it's 40 millimeters on the other axis. So let's define that. Move things out of my way. All right. So we need to cut an ellipse into... Well, this also makes life a lot easier because we defined the center as, that. Oh, dear. It's over-constrained. Oh, perfect. So this dimension is, we said 18 millimeters. And then this dimension is 40 millimeters. We do need to make sure that it is centered, so we're going to put this here, and then we'll make these 2 points symmetric around the origin. All right, cool. Perfect. Nice. Oh, I did that wrong. Sorry. It's these outer ones that are... No. Okay, hold up. It's going to be... I don't know what the radius is, so actually, we're going to define 2 points on the ends. These are going to be coincident with this. These are going to be 40 millimeters. Okay, perfect. We've now got our oh, wait. Oh. Why did hold on. Did not work the way that I wanted it to. Well, if it's 18 wide, it's a radius of 9 millimeters. So that's going to be 40 minus 18, or 22. There we go. 22 plus 9 plus 9. So 22 plus 18 will be 40. So yeah, that's the cut. There we go. Perfect. All right, so now we need to cut out clearance for these 2 mounting holes, up and down, so that those are... let's make sure this is centered. Those are, see, 14.5 millimeters in either direction. Okay, so those are 14 millimeters offset, and then we want a clearance zone of 20 millimeters. Of 20 millimeters, yeah. So we'll do 2 more ellipsoids. That. We said 20 millimeter, and the offset between the wall and the center is 14.5. So distance here is going to be 14.5. The distance here is going to be 14.5. We're going to constrain these as symmetric. Constrain these as symmetric. And then the distance here is going to be... Give ourselves 8 millimeters. And the width, we said we wanted 20 millimeters, I believe. Yeah, 20 millimeters, which 20 minus 4 by 4 is going to be 12. So it'll be 12. We'll just make sure that these are the same. All right, those are our cutouts for those mounting holes. All right, and we just need to do the one in the back. So the spacing from the rear is basically 20, more or less 27.5 millimeters, I believe. Yeah, let's say 27.5 millimeters from these back holes. So let's just put a line that we can reference, and these will be... Oh, I did that terribly wrong. Oh, I forgot to zero. It's like, wait, that doesn't sound right. Okay. It's more like 70 millimeters. All right. Okay. We got 70 millimeters here. That's like the center of this void we need to make. So what we'll actually do is just delete. Hold on. Make sure we did 26. We want to just delete the line, and this is. Remember, this is 26.5. It's almost constrained. What's under 2 degrees? Oh yeah, this line. Okay. All right. So we're going to. So what we'll do, we're actually gonna. Do that. Do that. Do that. Do that. Do that. Again, these are symmetric. Strain symmetry. All right, and the length of this is. Cut out a channel. Say 26 millimeters. And it needs to be. This 5 millimeters from center. So we'll say that this is actually 65. Means we can delete this line here. Perfect. And now we're fully constrained. All right. Perfect. So that is our 2 mounting legs that will turn into the mount for the pie. Is here. We still need to do the ones for the LiDAR. But we still need to research the LiDAR ones. Okay. Because it might surprise us a little bit. Because I don't know how off kilter this can be. Interesting. Okay. Doing a little think here. It's just back to Danish watching me, I think. So, yeah, again, questions about how to make soldering and how to make 3D modeling interesting. At least I can talk through the 3D modeling. But I don't know about soldering, still a mystery. But, or on how to make it interesting to watch. Yeah, so if we do this for the LiDAR, I think, oops. I'm also doing a lot of fidgeting with things in front of me and not showing it. I think actually we might just be getting away with it. Perfect. All right, yeah, let's actually define the mounting holes for the LiDAR now. Let's do that. So let me remove the mounting bolts from these. Then we have to make an executive decision on how tall these LiDAR mounts will be. Realistically, I think how tall the LiDAR mounts is going to come down to how tall the camera is. But we'll figure that out later. To make soldering interesting, you can always just burn stuff. Yeah, I guess I could just burn myself too, right? I'm actually pretty good these days about not injuring myself with my tools. Usually. Usually, the only I think the only tool related injury that I still or injuries call is stretching the definition a little bit, but I still have a horrible time not getting super glue on myself whenever I'm using it. It's always like, let me be careful, let me be careful, let me be careful. You know, okay, we managed to work, and then something just isn't lined up quite right, and I just go in there with my fingers to try to align something, and I end up with super glue all over my hands, and then my skin has white crust on it for days until the super glue falls off, or the skin grows and flakes. The super glue soaked skin, naturally falls off eventually, as your skin grows, right? Oh well. So the LiDAR is going to be fun because I'm figuring out the mounting arrangement, because we don't really know. There's not. It's got a bunch of. It's got a bunch of circular bits. So we've got that inset thing, but there's not a lot of good reference points. So what we'll do is we're going to define again four holes, roughly in the correct places. So we're gonna make. We're gonna assign this is basically this is the left, right. Actually, the right, or here, hold on. What does this actually look like now? Wow, this is actually inverted, right? Because we're looking at it from the front. So, top, rear. Why is... Oh, this is the direction you're looking at it from, right? Okay, so you're looking at it from... You're looking towards the left. You're looking towards the right. But this is actually the left face, right? Alright, so that means, or actually before we get to, okay, that's fine. Top, front, okay, so back to the sketch. We'll define this as the, the right-hand side of the robot, because the LiDAR is the motor is gonna be mounted off to the right. So we're gonna define a hole here, a hole here, a hole here, and a hole here. And they're not symmetric about the axis. So we're gonna come and define some central point. This will actually be the center of the LiDAR. And we have to figure out how all of these are relative to that. But what we do know is that these are vertical, and these are vertical. And this axis here will put a big horizontal line here and make sure it's coincident with this. And then these are going to be symmetric around this line. And so we got this. So we just want the spacing to always be there. Right? Okay. So let's figure out, and realistically, actually, these holes are a lot further this way than these ones are. So let's start with, hopefully one of these posts doesn't end up over one of the cutouts, right? So let's try to figure out the offset from center of these points here, right? So I'm going to try to measure from the center of one of these mounting holes to where the cables pop out of the LiDAR here, and wish me luck. And I think that watch that be. It would be surprising if it was an even number of millimeters, just because this is an angle. So, I don't think I'm gonna get. And again, this is also fraught with trouble, because okay, it's still too large. It's probably like 44.5 maybe. Doesn't have to be perfect, but. Again, we want to try to make it as perfect as possible. More than that. We're just going to say 44.5 millimeters and hope it's close enough, right? So we're going to define the distance here as 44.5 millimeters. Did I get that right? Really? 44.5. Maybe 43.5. 44 might actually be more betterer. Also, it defined how far these 2 points are away from each other yet, so let's do that. The spacing on these front ones is, and actually what we're going to do is we said we're going to make this, actually we haven't even defined the size of these holes yet, so let's make all these equal. We're going to define the radius of these as, what mounting standard are these? I think these are M3. These are M3s. These are E5 for M3 inserts. These are at least, oh god, I hit the vertical. Sorry. These are going to be, ooh, these are going to be horizontal with each other at least. And so the mounting of these are, how far apart are these? These are 73.5 millimeters, looks like. 93.5. No, more. I think 73.5 is probably close enough. So these are 73.5. I vote for burning stuff. All right. So just to confirm that this mounting is apparently correct. Well, I mean, yeah, actually, the hole shows up a little bit behind the cutouts for the center thing, right? Yeah, 73.5. Yeah, is that thing actually centered here? That'd be funny if it wasn't. No, we already established that this cutout thing is centered. Okay. But what we didn't establish is the. So that's about 75. Yeah. All right. Yeah. So the LiDAR mounts are. And that because of this distance thing here, we've defined where these go, right? So let's measure how far apart the rear ones are, and then the other ones are. Again, a little less interesting without me, so here, let me just give a small taste of what we're doing here. We're just trying to figure out how far these things are apart. Not the most terribly interesting work in the world, but we need it to make our 3D model. So right about, well, let me actually center things in view, right? 43.5, I think. Color me intrigued. Okay. Taking measurements so we can make models, right? Okay, so let me put the camera down so I can actually get an accurate measurement. And one hand on the calipers, one hand on my cell phone here, trying to. Oh, hey, Alejandro. Trying, these look like they're, yeah, 43.5 is my best estimate on this. All right. So we can define these as 43.5. We still don't know how far away they are from the center, but we're almost there. I can tell you that they are about 75.2 millimeter. 75. What happens if we do here? Hold on. 78.25 minus. What is the center between 78.25 and 72? Plus. You almost ready for aftershock, Alejandro? 72 and 78.25. 72. All right, 75.125. All right. We'll do that. 78. 75.125. 75.125. All right. Cool. Now we've got our mounting post for our LiDAR. Finally. Okay. Perfect. So now... I'm tired. Sounded for you, but yeah. So the kids tire you out, and then we're gonna go stand in, 20,000 person crowds for 4 days straight for 12 hours. Yeah. I think the printer's almost done. Yeah, printer's almost done. Okay. All right. That define. We can actually measure where the center is, right? Or that'll give us the. We'll need these numbers for later. 40.1.75. Yeah, we'll need those later. All right, so we've got this mock-up of the base, or this is the base plate, I think, that we need to mount everything to. And now let's pad this out 5 millimeters for the mounting hardware. So that gives us this plate that we have now spent a long time trying to figure out how to make, right? All right, so... So for now, I'm thinking, how? All right, actually, the printer just finished. So let me take the phone camera again here, and go check out the printer. Oh look, kitties. Printer. Pull the plate out. Give it the old bend trick here. Burn my legs because this is a heated. Ouch! Yeah, a heated bed. Burning flesh. Ow. Okay, I might have to give this a second to cool off. There it goes. All right. Which side? It's not burning. It's just uncomfortable. Really uncomfortable. There we go. Okay. Gross finger oils all over my print bed. Exactly what you're not supposed to do if you're going to do a subsequent print. There we go. Got our battery plate. Oh. Okay, well, at least they're durable. Peel that off. And return print bed back into the printer. spend so much trouble getting it freaking centered. There we go. All right. Okie doke. We'll quickly heat this up. What temperature is it set to? Probably only 400 degrees. Okay. All right. We need the threaded inserts. These things. Grab that. Come back over to here. Hopefully not spill everything. All right. So put the inserts in here. Inserts in here. Inserts in here. Move that. I'll line these up. All right, there. Get in there. There we go. Okay, now we can take the iron. And just push them in. Alright, actually let's go a little more. There we go. Needs to be a little more adjusted. There we go. And then one last one. Do. All right. This one needs pushing a little more. All right, cool. I think not quite flush. I don't think these new inserts are quite as thermally conductive as my. Oh shit. Okay. Well, undo that. Oh dear. Well, it's in there now. As long as the bolts are. No. Okay. Hold on. Let me fix this. Hold on. Yay! Burn. Stunning. Hold on. Let me fix this real quick. Okay. Oh, hold on. Let me grab my back goodies. Hold on. Okay. All right. Back over to here. All right. Back over to here. Okay. So we now have the 3D printed. We now have the. Wow. Tripping over myself. We now have the threaded inserts in the 3D print. There we go. Now we can mount this plate on the bottom of the robot. Let me clear off my workspace a little bit because I'm terrible at thinking. Oh, no, there. I won't do that. It's more of like the order of the things on my desk. Sometimes I don't do things in quite right order. So this is gonna go. Yeah. Hold on. This. Yeah, we're gonna hold on. Let's unplug this real quick. Okay, unplug that. There we go. So this goes in. Oh wait, it goes in. No, it goes in. How did I do this? How did I make this? Why are we here? There we go. That's how it mounts. I forgot. Okay. Why is this not quite sitting flush? Where am I? Who made me? Why am I here? Okay, yeah. So that plate sits in there, and that's going to be what we mount the battery to. It's just to give ourselves a little bit of a little bit of space against the base so cables can route under it, but also it's something that we can easily remove. Something we can easily take out so we're not actually gluing things to the robot frame. So let me switch back to the desktop here just so we avoid shaky cam, right? Find my countersunk screws. There we go. No, I see the baggie, but that is not what my finger landed on. Here we go. Our countersunk screws, right? And of course, I leave the normal screwdriver. There we go. What year is it? Easier access later on for issues of breakage. Yes. Okay. Boom. Alright, now we're going to put these screws in here and hope they work, and oh my god, they do! The alignment is maybe not 100%, but it's close enough. Desk cam, wake up fun. Now see, we can see little threaded inserts through the holes in the top. Means we can put our little screws in here. And because they're countersunk, they sit flush with the frame and they don't stick out. So we can actually put stuff right on top of them without having any sort of issues with things not being flush. That one in there. Super sleek. Thank you, Alejandro. I try. I aim for. I try. I try my best. Sometimes it works, sometimes it doesn't. But this, flush, no edges, smooth. No. All right. So put this back upside down, and I will go grab a Velcro strip real fast, or maybe we can nimbly scoot along over here back to my pile of stuff. There we go. Velcro strips. All right. So let me put it back on the desktop just so I have my hands free. And let's see here. Which one's which do I put? Okay, so the pokey one is on the battery, which means I need to put we're going to describe the Velcro as the pokey version and the fluffy version as the two sides needed. So the pokey Velcro is on the battery, which means I need the fluffy part of the Velcro in the robot. All right. Oh god, it stuck to me. It was a mistake. All right. So let me plug the Velcro, align the Velcro on here, then we're going to decide what. These are the scientific terms. These are the fluffy part of the Velcro and the not fluffy part of the fluffy and the pokey part of the Velcro. All right. Put that in there. Make sure we are. Oh god. No, I'm not ready. All right. Okay. There we go. So I will take a video. I will point the camera after I do this because it's a little finicky. little finicky. These are scientific terms. Okay. Get the battery BMS out of the way. And we'll put there we go. I think I've aligned it correctly. Oh, dude, I got War on the other. War Thunder, War Frame, War. League of Legends. I got War. Real War in the real world. Real War. Okay. All right. Total War. Oh, there we go. Running out of game. Okay, there we go. Fighting Mike as we speak. Oh, wait, as in Dad or wait, or be really funny if you got him to play video games. Really funny. But yeah. Okay. That'd be an achievement. Yeah. Wouldn't it? Okay. Okay, here, let me point the desk cam back at this. This is what we got. So, we now have the battery in here, and with enough clear, we'll leave it there just for a little while so the glue on the Velcro can dry. This week. Good luck. Mom will. I don't know about Dad. No. Okay. Desktop. Let's see if we can get this to work. Alright, battery. Yeah, now for the important part. Can we get the freaking connectors to flex well and good enough? Alright. Hey, there we go. Perfect. There we go. Alright, nice. So we got the battery mounted now, and we can actually fit our connector in there, and we tied the main cable down. Yeah, battery is in there, and we'll be able to pull the Velcro in order to take it off. And it's not stuck in any way. Perfect. Okay, you know, this calls for just a slight remote control test here. Oh God, only the live action. Okay. Okay. Cool. All right, let me plug the Pi Pico back in here and make sure I don't plug it in backwards, because that'd be fireworks. Do. There we go. Pi Pico back in here. And we should be able to flip this switch and not have things explode. Hey, they didn't explode. So, I'm going to put this on the ground, and now, see, I got the battery mounted underneath, so it doesn't fall out, and it's not just sliding around on top. So, let's put that on the floor, and bring up our control program here. Pico PiBot, source, virtual environment, we got tools, wake up my controller, tools, balancer, client. All right, start that up. Bring my phone back up, desk cam. Hopefully the controller connects. Hey, there we go. That connected, which means we can drive it around. There we go. All right, didn't break anything. All right, cool. That's enough of that. All right, back to the desktop. Okay, so that worked. All right, cool. So now we have a battery mounted in here, which is very nice. Although we're going to take that back out in order to get the mounting screws in for the plate that we're still modeling. But that won't be done printing for a while, so we'll still finish it. Then we can print it, but we'll worry about that later. But because all the cables are underneath, the cats now can't eat it. Because they haven't learned how to flip things over. Don't learn how to flip things over. Don't. Any plans to shield the battery from debris underneath? Maybe. Eventually. Just a second. Let me get back to this. Okay. So, okay, we tested the balance, so let me disconnect the controller. Not my headset. Okay. Perfect. Controller's turning off. We'll close this back up. All right. Perfect. So, we've got our mounting plate for things. And now we need to bring up the standoffs that we'll actually mount stuff into, right? So, let me switch back over to this Lakiwi, my other part experiment here. I think what I did here was... we're going to do this a little differently. So we're going to bring up the tabs here, but the way that the case is going to work on this for the Pi is we're going to have a full cap that comes down. We're not gonna try to sit it inside or anything. Which, I mean, we could do in the future to try to save some space. But it's not really worth it. So let's... So, you know, at 5 millimeters thick, you know, these are 4 millimeters thick, right? So we could cut out... We could cut into the surface here so the Pi sits lower inside this part. But just to make things a little simpler on us for now, we're not going to worry about cutting into it to inset things. Especially with the Pi. We'll just make a top mount case, essentially. That'll be a full coverage can that comes down over it to cover up parts. So the standoffs that we... So, okay. Well, I was actually tabbing over here for us to figure out how tall these standoffs are. And I believe, oh yeah, it was 3 millimeters because it's just how much clearance do I need under the Pi. So what we'll need, okay, so sorry. Well, I just randomly mousing over things. Okay, so now let's do these, bring up these standoffs. So we'll bring up these holes here, and we'll go back to actual drawing mode. We'll do that, do that, do that, do that. Then we're going to try to make these... And I'm having trouble again. Why did these not want to be concentric? I don't understand why that's failing. Anyway, we do know how large these are. We know these are 4 millimeters. So we'll just manually define these as equal. Then we're going to need an outer volume. Just make these 1 millimeter essentially, or 1 millimeter larger. So these will be 6 millimeters. Or we want a 1 millimeter wall, right? Missed one. There we go. All right, so we got that. Those will be our Raspberry Pi mounts. We're going to bring up the LiDAR ones a little later here. So, actually, I'm kind of curious how... Nah, we'll worry about it later. We probably want to make a little overhead mount for the LiDAR as well at some point, but we won't worry about it for right now. So let's pad this. These will be 3 millimeters. So this is... those are the Pi standoffs. We'll put threaded inserts in there. And then we need to figure out how tall we want to make the LiDAR. And in order to do that, we need to know how far up we want the camera to be. And in order to do that, we really need to figure out... Okay. So the camera mounts kind of like this, right? Or we're gonna want to put it in an angle. These are wide angle cameras, so again, because I originally did want to put this on like a pan tilt mount, but I don't really necessarily want to reprint this plate if I don't have to, because it is already as it is. Let's export this and figure out how much PLA we're already using for this. I mean, PLA is dirt cheap, so we really shouldn't be worried about this. Another plate. Bring over the top plate. Slice plate. It's probably like 100. It's 44. Okay, it's really, if we have to reprint it, whatever, it's dirt cheap. We shouldn't be worried about it. So just for now, let's actually hard mount the camera to the frame. And these are wide. This is a wide angle version of the camera, so realistically, I want to tilt it down just a little bit. That should give me a perfect view still out into the distance. It's fine for now. So how do I want to go about that? What we'll do? Okay, I think. How wide do we want to make this? So we want so the Polycam we know is 25.2 millimeters wide. It is actually how much vertical space do we need on the back? Because of the camera cable, we don't want to completely 90-degree bend the camera cable. It'll break. Okay, we need to give ourselves at least 32 millimeters. Hey, kitten, how are you doing? I don't know how I feel about you continuing to get on my desk. You are cute, but I'm afraid of you eating things up here. You know. Well, if you just sit there and look cute, that's fine, but don't push my little bolts and screws and nuts off the desk. That's annoying if you do that. That's annoying if you do that. Yes, just so everybody is aware, there is a Kimty on my desk. There is a Kimty. She is being very cute. Hey, Shigua. What are you doing? What are you doing? Kimpton. Yeah. Hi, baby. How you doing? Yeah. If you just want to be chill on my desk, that's fine. I've had to rearrange my apartment so many times just to try to remove things that they can eat from places they can access. But yeah. So back to this. We need 32 millimeters behind the camera. The way that we're gonna make the camera mount is okay. How are we gonna make the camera? Don't push my keys, you little silly cat. You're so cute. Oh my god. What are you after now? Just doing a sniff. Just doing a sniff. No, don't try to push the bolts off my desk. Oh, I full screened it. How do I unfull screen it? Oh, dear. Well, we'll figure that out in a second, but Kimpton break here. Hi there, baby. Oh, you want down now? Or are you just getting comfortable? Oh, you want down. Okay. We'll go over there. There you go. Alright, now how do I undo what I just did? How do I... F11? Hey, there we go. It's the same thing as web browser. Okay. Well, what we could do is we could just put an angled face on the front here, but don't know if I want to do that. Well, we can cut it to whatever shape we need. So we'll actually do the sketch on this side. No, sorry. No, I don't want to do that. Here, top plate, active body, pad 6, sketch. There we go. So how we'll define this is we will do it like this. We're going to, no, not a rectangle. We're going to define this. It's going to come up at some angle. Define this. It's going to come up here. So we're going to import this edge, that edge. This is the end of this bracket will be coincident on this line, or on the top part of the plate. This bottom part will be the same as the edge of the plate. We're going to define these two lines as parallel, just so that they have, regardless of where they are, they have the same angle, right? And then we're going to draw a... good night. Good night, Alejandro. We're going to define this. These will be perpendicular. All right, and then the spacing needs to be defined here. Okay. We're We're going to define this as, you know, some thickness. We'll say 5 millimeters for now. And then we'll define an angle here of 10 degrees. Or 170 from... Okay. That's funny. Whoa, what the heck? Oh no, rendering shenanigans here. There we go. 10 degrees. And let's figure out how thick we want this front section. So the PyCam uses M2 bolts, and going back to my Lakiwi parts here, because I used going back to that wrist mount camera thing that I did. How wide are these? How thick is this? How thick did I make this? Why can I not? Oh. Made it 4 millimeters thick. And I made these holes 1.75. What? No, I want to know how wide they are. That's fine. We'll just go in. No, that's not where I defined that. Define it in here. Yes, there we are. 3.5 by 4. Okay. So we did 4 just because we don't want to make this thing too fragile. Yeah, we'll keep it at 5 because we just don't want to make it too fragile, right? And then sketch. And we need... Oh, well, I really shouldn't have done this as a draft line because we actually need a solid surface up there. These need to be perpendicular. And oh, we need this back face we said to be 32 millimeters. No, we want the length of it. Yeah, 32. Okay. We'll keep it at 5 millimeters just for strength's sake. Close. Then we're going to pad this to, I think, 110 millimeters, I think. Oh. Cancel. Clear. Oh yeah, the wire's not closed. Of course it's not. Okay, I did not finish. There we go. Close. Pad this as reversed the other way. I believe it's 110 wide. Yes. Oh, but we're messing with the screws. Well, the bolts come up through the bottom, so that's not necessarily a problem. Although it does look kind of not aesthetic. Well, we got 6 millimeter bolts. The frame's probably at least 1 millimeter thick. Let's check the aluminum thickness on this. It is... get a good measurement on this here. It's 2.2 millimeter aluminum. Actually, it's not even that. It's 1 point. It's more than 1 millimeter. We're good because I have 6 millimeter screws to hold this down with. So this is fine. It actually we're cutting inwards on this, so it doesn't actually freaking matter. Yeah, because what we actually want is we need the camera mount only needs to be. Where to put the camera? Oh, there it is. The camera mount only needs to be slightly wider than the camera itself, really. Because, I mean, realistically, right, you know. So if we make it, really all we need to do is make sure that we have enough margin to put in the threaded inserts. And they're 3.5 millimeters wide. Yeah, we do need to give ourselves a little bit of margin here. So make it 26 millimeter, 27, 28. We'll call it 28 millimeters wide. And so it's 110 minus 28. Let's bring up our Python shell again. So 110 minus 28, 82 divided by 2. So it's 41. So we need to cut off 41 millimeters on each side here. So what we're going to do is we're going to define... We're going to do a cutaway via the top here. And we're going to import this edge, that edge. And we're going to do rectangles, not centered ones, just rectangles. Do that. We're going to do that. We're going to import this edge, that edge. Yeah, well, that's fine. These are going to be coincident. These are going to be coincident points. Okay. Let's do the same thing over here. Coincident points. Actually, what am I freaking doing? Hold on. This is a terrible way of actually going about this. Okay. So we've got this sketch. We know we want the thing to be 28 millimeters wide, right? So we're going to make this pad 28 millimeters, right? But what we ought to do is we just set the offset for where this pad goes, and then we'll be good. So we need to inset it by 41 millimeters. So the attachment offset for this sketch, place attachment offset position. So if we adjust the x-axis attachment point for the sketch, it should move, I think. Hold on. How do I right side? I just want to view it from this angle. All right, sketch. So we want to adjust the attachment offset. That's not actually editing anything. Hold on. Oh, recompute. Sorry. Sketch. If we negative offset by 41 millimeters, and why did it not offset? That's annoying. Recompute object. Oh, come on. I know this works. I just got to figure out what's not. Why is it not working? Placement. That can't be it. No. Okay, hold on. I'm trying to think. Placement. Position. Oh, that's not working. Okay, come on. Attachment offset is supposed to freaking work. Okay, well, if we delete the pad and we change the attachment offset, now it should work. Negative 41. There we go. Oh, no, that's not right. Not X. It's what? Z. Negative 41 on the Z axis. Okay. And then we save that. We turn it into our 28 millimeter pad. We reverse the pad. There we go. All right, cool. And we've added our tilt thing. And now it's not covering any more holes, which is good. Okay. So now that we know how tall this mounting jig is going to be, you can actually measure it from here to here. And if we take the ruler, we know that our Z is 31.5 millimeters. And so if we look at our LiDAR, how much offset does the LiDAR actually need to begin with? Because we're basically just trying to measure the tabs here out to the end of the motor so we don't pinch the wires any more than I already have. So at 31 mil, and actually we can't even. So 31 millimeters, which is 31.5 millimeters. So we'll just say 32 millimeters, just to give ourselves some room here. 32. We're actually, ironically, at the same length as these standoffs were. Actually, a tiny bit more. Which is really, really funny. I guess I could make it shorter by assuming that the cutting a channel into the under part of the frame here to let the cable come around, and then feeding it up through one of these. What is happening? Oh, she's playing with the 3D print goo. Okay. Which I could do that. That would be a more efficient use of space. That would save me 5 millimeters. So if I did 27, what did that look like? Honestly, not that much different. 27. Okay, well, let's make this a little more complicated on ourselves, just to try to see it work, Okay, what we're gonna do, we're gonna make the front side 32 millimeters. This should be all just unedited. Okay, stinger, sketch, delete that. This is gonna be the 32 millimeters. 32. And I need to put that in the right spot because this needs to be 32. Okay. All right, cool. Close. And what we'll do now is we're going to make a notch under here that's the width of the camera cable. And the camera cable is 16 millimeters wide. So we'll give an 18 millimeter cutout here. So we'll do a sketch. We're going to do a centered rectangle. But what we're actually going to do is we're going to import this edge. We're going to import that edge. And this point, will be on this line. This point will be on this line. We're going to make this 18 millimeters. Basically, the camera cable is going to route under the frame here, and it's going to pop out of this hole and come over. Even though there are some screws that we're going to want them out here, it's fine. We have enough margin, I think. And so let's do that. So close that. We're going to do a cutaway of 1 millimeter. Because I mean that's plenty. These are only 0.23 mil. We'll give it 1.2. Oops, that didn't quite work right. Oh, not 1200. No, not 12. 1.2. There we go. Oh well, I need to extend that a little more. Okay. Right. Delete the coincident thing. Okay. So we're going to... Actually, what we'll do here is we'll make sure that this is coincident. Perfect. There we go. Now that pops out of there. And we'll add a... Just try to relieve some of the stresses. We'll add chamfers of 1 millimeter. And that will... Oh, that not... Well, that's weird. What did that do? Really not... Oh! That's funny. Recompute. Hold on. Close. Sketch. That's actually really funny. Okay. It basically cuts into the extended bit out here. So, G, that... do these are coincident. Okay, close. Okay, perfect. And then now we'll do a chamfer on that, on this, a chamfer here. Select an edge. Come on, it worked before. There we go. So we'll have a chamfer. That'll give ourselves a little bit of stress relief on the edge. Actually, you know what? We can. I want to do chamfers just because they print easier. Realistically, we kind of want to make a curved part, but again, those are just harder to do over open air. So again, 1mm chamfer, because you can print a 45-degree easily. So the camera cable comes onto the frame. Perfect. All right, and so now let's do our... So that gives us, if we go on the right-hand side, we can now measure from the top here to the bottom here. Actually, no, top here to here. Give our ruler, that's 27.38 millimeter. So realistically, that even if we do it a little lower, that's fine. Because we've got this edge thing right here on the LiDAR. Oh, actually, no, I take that back. Okay, we've got this edge on the LiDAR, which we could technically mount over the camera if we want to. So we can actually bring this down to, so we do our 20 or 27.5 minus, minus another 5mm, I guess. So we'll just say, we'll do 22mm for now. And I think that'll be plenty. Yeah, so 22mm will make our LiDAR standoffs. If we need to adjust it later, we adjust it later. It's fine. So let's do our top sketch. And we're gonna import our LiDAR mounting tabs here. And we'll basically assign circles. Actually, and realistically, we don't actually want the cutouts like right here. So we'll actually cancel this sketch. Flip it over. Do this on the bottom. Because we'll actually just want to fill in these holes because we can. And we'll just put the cutouts for the we'll make these solid columns anyway. So bottom sketch, again, we'll save that so I don't break, just in case. Right, GX, that one, that one, that one, that one. Define. So if we're looking for 5mm, we want 7, 8. We'll give our, because these are gonna hold up stuff, we'll do 8mm posts. That'll give us wall thickness of 1.5mm up at the very top. And actually, honestly, let's give ourselves 9, because that'll give us a 2mm wall. Doop, doop, doop. These are all equals. Okay, close. They're not. It's not constrained. I missed one. Okay. Oh, it's not concentric. That's unfortunate. There we go. All fixed. So now we'll do a pad. This will be our 20, and this will actually be, we said 22. We're gonna go back to 27 because we need to do a reverse, and the thickness of the plate comes back at us. So now we can come in here and do that. Okay, that's okay. Now I can come back in here and put our holes in for the LiDAR, mounts. Oops. GX. Do that. Do that. Do that. Do that. And this one will be 5mm for our M3 mount. And then we'll just make all of these equal to each other. Equals, those are all constrained. We'll do a pocket of 5 millimeters, because that, or 4 millimeters? 5 by M3. So it's M3 by 4 by 5. Yeah, they're actually only 4 millimeters, but we'll do 5 just to give ourselves a, or actually let's just do 6 just to give ourselves a, just room for the bolt to come down through. Okay, so there we go. Now what we can do is to strengthen the interface, we'll go add some fillet. There we go. We'll add some fillet there, and we'll add some fillets around the outside. I don't think I'm missing anything. Some fillets just to smooth the model out a little bit. We'll do our filleting tool. We're going to define a 2 millimeter fillet. All right. Perfect. 2 millimeter fillet. And I think that's what we want for the top plate. Oh, we have to put in the mounts for the camera. That's what we got to do. I almost thought I was forgetting something. Okay. So, yeah, we need to do the mounting holes for the camera. Okay. So, let's look at the front again. Okay. So, sketch, mounting hole, mounting hole, mounting hole, mounting hole. These are all 3.5 millimeters. Equals, define 3.5. These are going to be symmetric with each other across that axis. These are symmetric across this axis. We'll define a virtual axis for this. We're just going to GX that. This is coincident. This is coincident. All right. These are symmetric across, oops. These are symmetric across this. What are you doing there, baby? Oh, hold on, let me get the cat. No, you don't get on my desk, please. Okie doke. All right, so those are all, when we're going to define the relationship of all of these to each other. We then do, so the spacing is, looks like 21 millimeters for the top ones. And then the next two down are it's like 12.5. You know, somebody, not 12 divided by 5, 12.5. Someone's probably got a Pi camera module 3 mechanical. Here we go. I get it right. So we got the spacing between holes is, well, it's 25 minus 2 times 2, so 21. Hell yeah, I got it right. And the vertical spacing is 14.5. Oh, wait. Oh, 14.5 between the edge, which means 12.5 between the holes. Haha, I measured it right. Wow, nice. And then we're going to import, so the distance between here, we want to give ourselves at least, you know, just a 1 Oh my god. Define a point. This point is vertical. The distance between these 2 points is going to be 1 millimeter. All right, and that secures that. And then the edge. So from there it'd be 23. Oh god, it'd be 23.862 minus 2, so 21.862. So let's draw another line. I'll do that. That's going to be 21.862. And the reason we want this is we need to cut out an area for the camera connector. And that, the width of that is basically 21, so we'll say 22 millimeters. Basically, that's going to bring us all the way down to here. And so the inset on that, oh, because the camera's not, I mean, there's hardware on the back of the camera, so I can't really make it sit flush. Okay, I may need to rethink this just a wee bit. I need to rethink this. Okay. So mounting the camera front coming through. There's hardware on the back of the camera. There's hardware on the back of the camera, so we can't just mount it flush with this standoff here. So what we could do is make ourselves some little standoff rings, essentially some spacer rings, like some 3 millimeter. We'd only need 3 millimeter spacers, or we'd call them 4 millimeter, 3.5 millimeter spacers, just 3.6 millimeter spacers, just to make our life easier. And as much as I would like to embed them into here, like, I mean, come on, it's we'd have to do supports to keep it clean vertically. Another, no, that's not really another option. It's already slanted, or I should say another option would be to cut out space inside here so the camera could mount flush. And I'm thinking about that. Let's actually see how that might work out. So we know that the clearance zone is 4 millimeter around the camera. So if we're assuming, so this is 5 millimeters thick, recall, right? So actually, yes. So since these are cutting all the way through, we don't actually need to worry about this other stuff. So that can go away. That needs to stay. That goes away. All right. So this is a pocket. 5 millimeters thick, because it's 5 millimeters thick. This is where our little threaded inserts go. But if I recall correctly, a M2 threaded insert. I believe I did. Yeah, I think they're 3.5 by 3.5 M2. Let me look. Yeah, it's at most they're 4 millimeters thick, right? I think I bought the 3x3 ones. Did I pick this? Is this what I bought? I'm trying to purchase another no, those are not the variation that I bought. No. Which ones did I buy? I think I probably bought M2 by 3x3. Here, let me pull this. I don't want to show you my order history, so I'll pull this into a different window here. Orders. Okay. M2 insert. Okay. M3, M4, M2 by 3.5 by... Oh, 4 millimeters long. Okay, so that's fine. So we're 4 millimeters long on the threaded inserts, which means we have at least a millimeter inset onto this. That we don't actually really need to use that. So now we're going to come back with another sketch, and we're going to define the we're going to cut into it to define the clearance zones. And so we're going to re-import these edges here. And that will give us... so what we're going to do is we're going to design a cutout around this to give ourselves the ability to mount this. And we're going to try to do some what do you call them? Chamfers, just to try to make this print without supports. So let's do our thing here. So let's define an edge. So add this. I'm here. I'm here. Come here. Nothing. Oh, there are a couple things that mount between the holes. Ugh, it's annoying. So these need to actually come up above a little bit. How far past center? Almost to the top. Okay. These are actually going to be... We're going to define points here. On the edge, these are going to be coincident points, but they're going to be vertical of these. These are going to be horizontal. These are going to be vertical. 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 I think. Not quite. We'll do that. Not quite. And so we'll actually define a drafting line between these two. We're going to say that these are... we'll give it all the same treatment. I'll do that. Do that. These are vertical. These are vertical. Okay, so back to drawing. These are going to be horizontal. These are going to be horizontal. And the radius is going to be 2. That doesn't give us much wall. So the radius here is actually going to be 2.5. 3.5. That would give us... Alright, it's got to be... Here, we'll do a formula. It's got to be 3.5 divided by 2 plus 1 millimeter. So 2.75 millimeter. 2.75. I gotta find whether... Do another drafting line between here. Line, drift it. No, we don't actually want these to be vertical. We want these to be vertical. We want these to be vertical. 2.75 and 2.75. Okay, cool. Got this. Back to the real lines. I'm gonna do this. Ow, cat. It's my leg. Oh, it's looking like a puzzle piece. Oh no. There we go. Define 1 millimeter, define 1 millimeter. Okay. The question is whether that'll be enough to keep it out of, so if we do 2.575 millimeters away from the center, is that enough to clear some of these components? it looks like we ought to be able to clear most of the components with this kind of cutout, I think. Be pretty freaking close, though, I'm going to be honest. It's going to be pretty freaking close, but that's fine. So if we do this as a cutaway, let's do this as a, how tall are the tallest of these components? 2 millimeters. 2 millimeters is plenty. Actually, 1.8. Do a pocket. It's going to be... Well, that's actually kind of cool looking, but 1.8 millimeters. Yeah, the question is freaking printability on this, right? Is how are we going to actually print that? Hey, no. Get down, kitty. You're cute. You keep trying to break my stuff. I don't like that. That's not good. No, you gotta get down now. If you're gonna break stuff, you gotta get down. Okay. Well, how well is that gonna do? Well, we can always compute what would happen with the supports, see what happens, because some of these is like these are kind of just like printing over open air, which is not great, but that's fine. So it's our cutout for components. We're going to do another sketch here to to allow for the connector. So another sketch here. I should have made this a bolt-on component, I swear. So we need to, so from the top axis, zero that. We need to do so starting at 14 millimeters from the center of this point, we're going to do a centered rectangle. And so starting at 14 millimeters and basically going all the way down to this edge. And it's say 22 millimeters wide. That's interesting. Actually, sorry. The not quite 14 millimeter. We'll keep the 14 millimeter thing in mind, but the actual connector starts lower. The actual connector starts at basically 15 millimeter from center to top. 15 millimeter, and then we need to define this other little rectangle here is, just need to do a cutout. Do a actually, is that wise? Hold on. I said 21, right? Or 22 is our ideal, right? So do that, do that. Or what? 22. Oh. That's the same. So hold on. The little bits here are 15 millimeters wide. So this only needs to be 15 millimeters. And we'll. Okay, cool. Close. We can cut these down to 3 millimeters, I guess. Actually, sketch 14. We'll delete that. That's 3 millimeters. So make a pocket of 3 millimeters. Okay. And that allows the camera connector. Although that does kind of hilariously break our this thing here. Just need to clean up this bit here. Oops. We might as well just delete that. We might as well just use this point. Where'd you get that? What is that? Where'd you get that? I don't like that. Okay. Yeah, there we go. That will allow the cable to pass through, and it is a little funny down here. But how are we going to model? How are we going to support this? Because we can't print over thin air, right? So, what to do? Well, at least let's load this up into the printer and see what happens. Because now this is pretty, well, I don't like these little hook things right here. It's a little ugly, but it adds a little character. I don't know. Front. All right, so this is the outside of our print. This is the LiDAR mount right here. This is the Pi mount. Looks like they're pretty decently spaced from each other. So yeah, let's see what happens now. So export, top plate, replace, come back in here, reload from disk. All right. So if we now we're gonna have to figure out how to auto support this. So hold on, let's just arrange this. Let's turn on auto support. Tree auto slice plate. See what happens. Doesn't look like it actually tries to do anything support-wise. Remove small overhangs. Harm. Threshold angle 30. Well, okay. What if I turn on multi-layer supports? We'll add a pet G as our interface material. PTG. Yes, change this automatically. Slice. How many filament? Oh boy, 52 filament changes. That's disgusting. No auto supports for me. Okay. We'll do painted supports, thank you very much. All right, so I told you, kitten, I'm messing with my cables. All right. It would have been easier just to smack the camera onto the back of this. Oh well, I wanted to make this difficult, I guess. Unintentionally made this difficult on myself. All right, so support painting. We'll start with fill on overhangs only. We're gonna put some support there. Put some support here. Put some support there, there, and there. Nice plate. Now it's 56 filament changes. That's ridiculous. Oh, manual. Tree support manual. Slice plate. 20 filament swaps. It's going to spend a ton of time. So, oh god, because we got to print the tower. Yeah, we're going to waste 51 grams in the model. Flushed tower. Oh boy. Kittens are going to be loving this. 2 hours 55 to print. Wow. Alright. I made this hard on myself, didn't I? I really did. So 20 filament changes. It's gonna be fine. It's gonna be fine. I gotta print a bunch of filament there for what? Why is it printing overhang there? Oh, those. Okay. So what we're going to try to do, we're going to try to re-engineer this just a tad. We're going to try to get rid of these overhangs, per se. Or at least get them away as a unique overhang problem. Because, I don't know. It's not very printable. Okay. Let's see what we can do here quickly. So we're going to delete this line. Oh yeah, it's fine. Stop. Clear. Do that. We're going to delete this line. Delete this line. I know the thing isn't closed. It's fine. I know. Keep that 15 there for whatever freaking reason. All right. So define that. Get these edges. And then we're going to need to define a this. That, yeah. around with this over here. Okay. What does that do? Actually, that probably made life worse, because we still gotta cut out stuff from up in here. Right? Anyway, close. Again, we're just trying to get rid of... So again, if rather than doing this, if we did a chamfer on this edge... Whoa, that's really broken. Put a chamfer on this edge. If I did fill it, is it less broken? It's less broken if I fill it the thing. 1.1. There's still some troubles with it joining edges in FreeCAD. But, I mean, that should... That's still a print. Okay. Okay. Sticking around with FreeCAD, hoping we can make things work. Let's try to, yeah, I mean, what I really want is just chamfer this edge, but the computation of it is really breaking badly. So... Oh, well, let's see if this helped with our problem anyway. Or let's see if this helped at all, you know. Probably not much, but let's just see, you know. Prepare, reload. Load from disk. Support painting, overhangs. That. Yeah. Oop, doop. Doop, doop, doop. Slice plate. Four filament swaps. So they're kind of localized. And 75, wasting 25 grams of filament just to do this stupid thing. All because I didn't want to make it into the back. Oh, hubris. My hubris. Actually, you know, we could re-engineer this a bit. We could always mount the camera further down on the back. We just cut out the back of it, right? You know, let's see. Okay, so let me save this file here. 3D modeling, Stinger, compress, add to archive. Activity, what the heck? Huh, hold on. All right, fine, we're gonna do the worst kind of backing up. Copy the file somewhere else. Okay. So yeah, let's backtrack, and we're gonna delete all of this cutting into the face of this that we did, and come in from the backside, but free up space on the bottom to bring the cable up, and just this will be, you know, we'll have a hole here, but it is supported on the other sides and makes it so much easier to print. So let's just go ahead and do that. So we're gonna delete pocket 5. The sketch, pocket 4, the sketch, sketch 12, yes, delete, no, delete that. Okay. Show you the printability metrics. So that would be a cool thing, honestly. That would be really cool. Okay, so we're here. We're going to work on the back. So what we're going to do, we're changing this up so the camera just bolts to the backside. Which just makes it so much easier to print, because rather than having to cut into the face and have all these overhangs, we can just pop the holes that we need, and it prints fine. Because okay, so, or we might need some supports for the top section, but it's fine. All right, so let's redefine our holes here. So we'll do our draft line, import our edges here. This is just our virtual axis that we build the camera mounts around. Okay, so we got that. These are going to be all equal in radius. So we assign this to be equal. We define this as 3.5. These are symmetric across this axis. These are symmetric across this axis. These are symmetric across this axis. All right, and that gives us our thing here. We're going to add a drafting point up here. This is going to be vertical. This is going to be spaced by, this is going to be spaced by, well, realistically, we only want to, if we really want this to line up and be really pretty, we just delete that. And then we'll do 2 millimeters here. Well, that makes a really thin edge, which is, you know, not great, but how far are these? You know, no, that doesn't help. That's not a very good. We want to make sure we have a decent wall thickness. Just it's fine. We'll do vertical of 1 millimeter. We need to make this vertical. All right. Remember, we do our spacing of 21 per the metrics. Do our spacing of 12.5 per that. All right. And now we define our cutout. We'll do a centered rectangle. That is where the little actual camera sensor goes, because we got this camera sensor in the middle, right? And the width of this camera sensor is at the thickest point. We're looking at, it's actually the little connector goes further to the side than, you know, it's 10. Does it actually give us an offset of the, it really doesn't. Sorry, the little camera connector on to the side where the plug is on the module, it actually extends out slightly past the camera. So we're looking at, so they claim, do they actually define, they define how wide it is, but do they define the offset here? Like how far from the side, or how far, they don't actually define this, it's 8.9 millimeters wide, but how inset is it on either side? It doesn't actually look like they defined that, which kind of sucks. So we'll take a measurement ourselves and then, you know, underestimate how far away it is just to give her. We'll do a larger cut. So we're gonna say 4.4 millimeters in from. So if it's this is mounted this way, so this will be 4.4 millimeters in from that direction. And then the camera is we'll also, just for symmetry, we'll also say 4.4 on the other side. Which it already is symmetry. 4.4, I said. Okay, that's fine. And then there really isn't much from the edge of the board. It looks like it's a little inset here, so we'll give this a millimeter. Well, this is like 0.6 millimeters. And the camera module extends below. As we can see, it extends 14 point. Basically, it's going to be 14.4 plus, or 12.4 plus 10.8 divided by 2. So 5.4 plus 12.4. So 12.4, it's 17.4, 17.8. So this is officially 17.8 from, you know, the top, or from this top mounting hole. If we actually go in with the I mean, that is accurate, but just from a printability point of view, let's give ourselves like 19 millimeters or something, just to give ourselves a little more fudge room, right? We don't need it to match, you know, exactly. All right. So that actually serves us well for our, for the, oh, Jesus. I forgot to delete the, okay, well, we can reattach the sketch. We want to keep the fillet. We don't want to keep this. Jeez. Oh, that's going to be hard. Okay. Let's see what happens. Delete the chamfer. Are you sure? Following reference objects. Oh, Freakhead crashed. Brilliant. Start. I don't want to recover the Kiwi parts. I don't care about the Kiwi parts. There we go. All right, let's delete. What's pocket 2 again? Oh, that's the tops. Okay, chamfer. That's that. Okay, yeah, we'll delete the chamfer. Cancel. Reference objects. Okay. Clear. Oh dear. Okay. Yeah, sketch. Oh, that made everything worse. Okay. Never mind. We'll just leave everything as it were. I need to chamfer of 0. God, it's gonna freak out at me for that one. Okay. Damn it. I wanted to make this easier on myself, and I made this harder on myself. Okay. Because I don't need this bit anymore. And you know what? It's funny. Okay, it can't be that hard. Okay, we'll try this again. Delete the chamfer. How hard is it to reparent this? Attachment support. This sketch was the towers. So what we need to do now is attach this to, oh geez. Actually, let's undo the deletion first. Sketch 10 was a flat face map on the bottom of this part. So we'll delete the chamfer. And we'll take pad 8 sketch, and that's going to be a flat face map to pocket 01. Okay, and then it's a flat face mount to the bottom. Okay. No, what the hell? Okay, no. Hold on, I'm still working. Attachment 3D. Cancel. It's going to be a flat face. Hold on, oh. They're not in the right spots anymore. Recompute. Object. Map mode. Solid. Okay. There we go. It reattached. Perfect. It's still not showing there because this sketch is broken. Oh, there it goes. Cool. Managed to delete that chamfer. Okay. Now what we need to do is delete that pocket, and we just need to delete this pocket, right? Yeah. Okay. Come back, sketch. We're going to redo all of this again. This is going to be a flat face mount to pad 7. Okay. Recompute object. Okay. All right. Pocket 2. Cool. Clear the errors. Nice. Awesome. We have our fillet. We've removed that channel on the underside. We've come back to our sketch. Perfect. Nice. All right. Oh, God. Thank you. Okay. So we'll make a pocket out of this. Oh, wait. Sorry. We need to reselect our active body. Make a pocket. It'll be 5mm. Perfect. Okay. There we go. We've made that. We've removed the cutouts in the bottom. We now need to, because this distance now is 27.8mm, and if we look at our camera connection here, we really do want 32. Basically, you know, it's just how much are you willing to bend the camera cable, right? And so I'm thinking I don't really want to bend the camera cable more than, say, about 31, 32mm. We'll say 31, just to make things a little tighter. So, which means we need a 5mm cutout aligned with this into the base. So we're going to do another sketch on the top. And do a sketch up here. We're going to import this axis here. And we have said multiple times that we know that the camera cable is only... we said 18 millimeters, right? Yeah. So that's going to be a centered rectangle. So we're going to make it 18 millimeters wide. We're going to make this coincident on this plane. And then we're going to cut the camera cable. Oh, we're gonna make this 10 centimeters. Yeah, that'll give us ample room to route the camera cable back around. So, alrighty, perfect. Close. We're gonna do a pocket again. There we go. Let's place the camera cable to loop back around. We're gonna chamfer this. Okay, that's fine on that. We're gonna chamfer this. Give ourselves a 5 millimeter chamfer. Doesn't like that. 4 millimeter chamfer then. Okay. Okay. And because of the chamfer, we can actually shrink the cutout. We'll do this to like 6. Yeah, there we go. Chamfer. We can always set it to like 4.9. As FreeCAD has trouble joining the thing for some reason. All right. So we got our fillet. We'll do our fillet up here. Actually, how much fillet was this? Was this a 2 millimeter fillet? All right, yeah, this is a 2 millimeter fillet. So we're going to redefine our fillet. We're going to also add these 2 edges. And we didn't actually add edges. Select, dupe, dupe. Okay. Clear that. All right, perfect. We've got our, oh, we missed one edge. Okay. Select, let's do that one. Okay. That's fine. Oh, we missed that. Is it, wait, is it kicking out our other stuff? Is it kicking out other edges because I'm filleting that? No? Okay, we're rounded on all corners. Hey, there we go. Perfect. All right. I think we're finally ready to print this thing. Oh, wait. No, we're not. We'll show that. Yes. Wait. There we are. Yes. Alrighty. Finally ready to print that. And we can actually... Now there are no printing over voids, assuming that we feel that we can bridge this without too much sagging, which we probably can't. So one thing we can do is, honestly, I don't even, we'll print it. I don't care too much. It's fine. If this central section gets busted, whatever. It should be able to bridge, what is this, a few millimeters? Well, it's not a few, but ruler, wow, that's not right. Yeah, can it bridge? I'm pretty sure we can bridge just a bit over a centimeter. I think that's fine. Although now we do have the camera on the back, so it does make it a little thicker. So we'll have to see. We may have to print a couple of spacer rings for the LiDAR, potentially, if everything goes wrong, but that's fine. So yeah, so let's save this. Export STL, Stinger, top plate, overwrite. We'll come back in here. Undo reload from disk. Yeah, we got a much different shape now. All right. So now we can say slice plate. And yeah, 1.5 hour print time instead of 2.5 hours just from filament swaps. Okay, so yeah, because this will print. How stringed is this going to be? Yeah, there. Ugh. Yeah, it's going to print this one little string right here, and then start building up as we go. And that might cause problems, but theoretically it'll be fine. Although what we could do just to make more certain, because it'll bridge better if it has, you know, some friends, or the strands next to it. So what we're going to do is we're actually going to adulter the face a little bit. So we're going to assign... this is a little rough. We're going to assign... Okay, hold on. We're going to try to use a subtractive volume. So that will be a subtractive box. We're going to try to attach said box to this edge. Okay, good. Actually, no, not good. Oh, shoot. Recompute object. Chamfer. Okay, front. Try to do a subtractive box. The box shall be attached here to this point. There we go. And the box is however much we defined things as wide. So if we go into, not there, here. So we defined this, oh, well, we didn't actually truly define the width, but you know, it's 12.2 millimeters. And we know it's 12.2 millimeters. Okay. So we go back to our subtractive box here. It's going to be 12.2. It's 12.2, 12.2. Oh my God, please. And the offset in the X direction. Actually, you know what? Cancel. I'll delete the box. It actually makes more sense to do it there. Reflect the box around the z-axis. So we'll do 180. Oh. That didn't work. There we go. 180. And we call it 12.2 wide. We're in height because everything's broken. All right. And then we subtract 10 millimeters off something. All right, probably the Y. 10 millimeters. Okay. And what that does is that kind of doesn't do what I thought. Oh, I did it backwards. Haha. Okay. Oops. I wanted to attach it to this edge. Okay. Box. Attach here. We want to do 12.2. We're going to revolve it around the y-axis by 180. And we're going to subtract 10 millimeters from it. In the y-axis, we're going to move it forward. Yes, there we go. Okay. There we go. And now we have sliced an angle relative to this plane. But what that'll do is, if I export this again, and overwrite this, close that. Back to the slicer, prepare, reload. See that this changed here. And then when we slice it, I mean, the print time's the same, but what we can notice now is that we print this whole area collectively, so the layer lines will stick together better. It makes it just more printable. So we're ready to print now. And so we can do export. Or we are in the slicer. Remove the PETG. Slice plate. Print plate. It'll take an hour, and it'll take... Oh, the stream will be over by the time I finish printing that. But, all right. So we got that part. What else do we need to print? All right, so, I mean, the big one, I mean, the other big one was we do have our battery printed, our battery mount printed. And, which is good. We don't really need to worry about the other thing. We already have the 3D printed bit that holds our logic board in. So we're not really worried about that. So what next? I think what we could work on next is while we wait for this to print, the last little bit of thing before we start getting into, not the last little bit of thing, there's still gonna be more things, but things to think about before we get into ROS anyway, will be, I think we need to write Raspberry Pi code, or Raspberry Pi Pico code that we already have, controlling the motors, but we will need to migrate that to being over USB and rather than over Wi-Fi. And so that'll be some fun. But what I think would be cool next, since we haven't demonstrated it, is, we want to be able to see something happening after we get the LiDAR hooked up. So I think what we ought to do is we'll jump back into the PicoBot code that we were working on before, and now we will add support for the LiDAR. We'll decode the data stream coming off the LiDAR, turn it into sample packets, and then we'll send that out over we'll send that out over UDP so we can visualize it in Jupyter notebooks like we've been doing with some of the other stuff. But yeah, so I think we ought to do that. And that will be cool. Rather than visualizing the we'll keep the IMU data, but it'll be a little different. Yeah, if we get a motion packet, let's do that. So let me hook up. Well, now that I've gone and disconnected everything, now that I've gone and unscrewed everything from the LiDAR, right? Now we're gonna go plug. We need to put the LiDAR on something, right? Okay. So. I guess we're bolting our mounting screws back to the LiDAR, huh? So we can plug it into the Pico here. We'll just put these little bolts back in. I think these are M3 by 10 screws, so it'll be nice to get some of these back. Alrighty, so put these on, hold that in place with my fingers. Fingers. Put that one in. Alrighty, so bolts are back into the LiDAR. We'll plug the LiDAR in. So we do that, put those in. We've got the everything getting stuck on everything else. Hook up the LiDAR data cable. Hook up the LiDAR drive motor cable. Alrighty. So we got that going. And what I'll do is we'll just, well, thing's gonna have to sit on my desk here just because I gotta get the debug cable into it. And actually, let's unplug the Pi Pico so we can get the debug cable plugged in. So if it's mounted like this, I think I've told myself it's orange down. Orange up, orange down, something. Which way is it? Ah, what's that? It goes this way, which means it's orange down. Okay, there we go. Just plug in the debug header back into the Pi Pico. So we'll send that out. Plug our Pico W back in. Pico 2W. Okay, cool. Pico 2W installed. Get the debug cable. Over here. Alright, plug that in. Is that the debugger? We got debug. Alright. Ow, ow. Cat's chasing the freaking USB cable. Button, not button. Sagwa, no, don't do that. Do a little bitty Kimchi break here. Little bitty Kimchi break. Kimpton break. How bad be? How you doing? How you doing? Do I get down? There you go. All right. Oh, okay. Put that down. We'll put this here just for now. We'll minimize that. Do that Pico PyBot, VS Code. And close some of these things. All right. This is not going to reconnect. So opening remote, close remote connection. Open Pico PyBot. Close that. Alrighty. What are we doing here? Alright. So, we need, actually, let me go grab a drink real quick. All right. Oh. Okie dokie. Okay, so we need to actually we'll just do our good old split screen here. Drag this over. So we need to add code for the LiDAR. And so the way that we're gonna do that is somehow no. So we've got this task. That's the tilt sweep task. Never mind. We have this task that I started creating that is the LiDAR task. But what we need to do, so the modification that I think I may have made off camera is I added this GPIO set function, UART function select UART 0 pin 17. That's the pin that we decided would be the LiDAR data. It is the UART 0 receive over on GPIO 17. That's where we connected the LiDAR to. So the LiDAR then runs at, I believe I think the XV11. So we're looking at the XV11 LiDAR. That might be 2300, but no, it is 1500 baud, EV3 dev. So we just need to look at the... is it 1500 baud? Is it really only 1500 baud? Sorry. Oh, EV3 dev, as in somebody attached a XV11 LiDAR to an EV3, or a Lego Mindstorms EV3. So, let's see. I just need the protocol, which I have worked on, honestly, I have worked on before. Like, I actually have GitHub, Nito LiDAR. I have this C code that I wrote a long time ago that is terrible. This is, but this actually does implement the protocol for the LiDAR. So you got XV11 LiDAR. Let's see if somebody actually. Let's see if I can find an article that describes the protocol so we can kind of re-engineer this from scratch, right? Things I learned interfacing the Nito LiDAR. Oh, that's gone. This is also an old LiDAR, right? See if the protocol is... Nope, that's the teardown. Let's see, XV11 LiDAR protocol. Underlying XV11 protocol explained. Nope. All right. Whoa, wait, okay. Now that we're at the code bit, what's the C++ keyword for binding variables to rerun the lambda when you update I'm assuming that's the value that it's tied to. So, are you thinking like properties in languages of those like .NET properties or Objective-C or Swift like properties where there's a function that's run if you like set like if you do like object.value equals something, does it call the set value function? Like rerun the lambda when you update the value it's tied to. That'd be... I don't think there's an automatic thing to do that. Or assignment functions. I don't... if you want to explain a little more. Come on. I could also just use my existing code and move it over to oh look, somebody made a stand for the LiDAR. Mika. Oh, just looking for the wire protocol. Come on, man. Obviously, Google pulled it from somewhere. Oh. Oh, here we go. Well, on it'll yield 90 packets containing 4 consecutive readings each. The length of the packet is 22 bytes. The amount of readings for a total of 360 degree is 1980 packets. Each packet is organized as start, index, speed left, right, data, data, data. 4 readings. Each are 4 bytes long, organized as follows, and then 2 checksums, which I think is CRC16. Oh, not really. Okay. Fun. Start is always 0xFA. Index is the index byte into the 90 packets, going from A0 packet 0 all the way up to F9 for packet 89. It's a 2 byte RPM. 4 readings, each is 4 bytes long. Organized as follows. It's going to be a flag byte or distance, 255. Oh, it's coded on 14 bits. Oh, it's 14. Okay. It's in centimeter. It's in millimeters. And we got the upper few bits are the distance. Byte 0. When bit 7 of byte 1 is set, indicates the distance cannot be calculated. When this bit is set, it seems that byte 0 contains an error code. If bit 6 is a warning when the reported strength is greatly inferior to what is expected at this distance. This may happen if on low reflectance. Okay. That's fair. So if we got 1980. Well, we'll have to send it as a couple of different. We'll have to split it in half anyway. Problem is we basically gotta detect whether we basically have to buffer up data, or we have to buffer up data and try to find the first valid packet we see. Otherwise, wow, I'm really not explaining. I'm starting to get really tired. Okay. But we gotta wait for this to print so that we can actually, install it tonight. Another hour and a half, right? So it'll finish just before midnight, right? It's estimated it'll finish at midnight. That's funny. Okay. Okay. So we need to add sorry. We need to add a UART interrupt so that we can not use a busy loop. And then the kitten is coming back up onto my desk. Hi, Kim T. Are you going to be good? Or are you going to attack all my stuff again? You're being cute right now. I'll give you that. You're being cute. Well, if you just want to sit there and look, that's fine. But I know you like messing with things. Looking for things that are fun. I know, because you're a little kitten. I get it. I get it. I get it. Got a kitten on the desk. Hey there, baby. Yeah. It's not that you being on the desk, it's just you pushing stuff off the desk. That's all. Okay, so realistically, all we got to do is we're going to all right, so we need to add a UART interrupt so that we can get We don't have to busy wait when we're getting for data from the LiDAR. And then what we need to do is basically start scanning for this at 0xFA byte, and then find essentially the first valid packet. And then that'll be, we assume synchronization at that point. And then we will decode the data and then pack it all up into a single packet, and then send it off to our display program. And so, assuming that, what would be 4 bytes times 360 samples? So 1440, which is just barely enough to fit inside a single UDP packet. We don't really care about the speed or anything of the LiDAR, until other than we need it in order to regulate the LiDAR's RPM. But other than that, we're good. So we need a signal strength. So yeah, we'll send these 4 bytes of data over to Python. Okay, checksum, and then UDP handles all of our checksum fun stuff for us. All right, so what we can do is we're going to re-enable. Wow, I just blanked again. Okay, we're going to re-enable semi-hosting to get printf out of the controller. And then we're going to do... figure out what the kitten's doing. Okay. Okay. How goes the next layers? Interesting. That looks a little gunked up over there on the edge, but we'll let it run and see what it does. Again, PLA is cheap. All right. So UART interrupt. Wow. I can't. Oh my god. UART interrupt. High Pico 2. UART interrupts. Use the UART libraries. UART FIFO usage. ISR context. Implement the ISR. Read from the FIFO. You know, I guess we're going to need circular buffer implementation. Reduce overhead, enable the UART FIFOs. Wait, I mean, sure. Okay, back to the PyPico CSDK guide. PyPico CSDK guide. Okay. So we're going to say... There we go. So UART. UART. Hardware UART. That's what we want. Ooh. Library documentation, hardware UART. There we go. Sample. Define UART IRQ number. UART. How do I define a UART interrupt? Set IRQs enabled. Instance UART. RX has data. How do I define the function for the interrupt? Because you would always say, you'd say add IRQ handler. That's a bit different. Okay, anyway. Alright, so UART init. UART set format will be UART 0, 8 data, 1 stop bit, parity none. Actually, it's 8, not... Okay. 8N1, UART set format. Function always enables the FIFO, configures to the default format. Okay. 8N1, baud rate, that's fine. Always enables the FIFOs. I need to be able to assign UART interrupt. So that's fine. So can I interrupt? How do I set an interrupt handler on iPico? iPico set interrupt handler. I don't want. Oh God. C++. AI doodly do. No. iPico. I guess set UART interrupt handler. Enabled IRQ set exclusive handler. Set IRQ enables true for. Alright, set a service function on RX is readable, get share. Okay, that's fine. IRQ set exclusive handler. I see. Okay. So, that's how that works. So what we can do is we can say IRQ set exclusive handler UART 0 IRQ handler T, and the fun one is that we can always just do an inline function like that, and then UART IRQ set enable. What is the distance here? Okie doke. Then we're gonna say void UART 0 RX interrupt. Let's say that. All right, UART 0 interrupt, which will give us our data. And what we can do is we can use a wow, jeez, I'm so blank. Okay, well we're right, we're running free RTOS, so we can do free RTOS stuff. So free RTOS stream buffer. Stream buffer implementation uses direct text notifications. All right. Uniquely, the stream buffer implementation built up stream buffer is only one task or interrupt. Okay, stream buffer send. There we go. All right. So we need a UART stream buffer. So we're gonna say stream buffer. Okay, hold on. Include stream buffer. Let's say stream buffer. Handle T. UART or LiDAR buffer. Pointer. I'm gonna say void setup. Nah, not yet. We'll move it to a new function when we get there. Okay, so you stream buffer. So we're gonna say UART, or say, sorry, LiDAR buffer equals X stream buffer create. Buffer size bytes, trigger level bytes. So say, give ourselves a 2 kilobyte buffer, and then, is there a stream buffer peak? Buffer receive. Bytes available, trigger level. Well, anyway. Anyway, okay. You are 0. Interrupt. Yeah, we can set up LiDAR buffer. Okay, cool. LiDAR buffer. Your 0 interrupt is just lift this set or whatever. We need is base type T, X higher priority task woken equals PD false. How's this going? That's fine. All right, so we're gonna say X. That's fine. So we need to look at the. Let's look at the SDK. Figure out if there is a FIFOs are enabled. Maybe we can look at the FIFO depth. FIFO hardware. Okay, well, anyway, we'll say while, no. So we'll say, so the interrupt handler will be, we'll just do one at a time for right now. If, no, well, so we'll say uint 8 buffer 16 or int I equals 0, I less than size of buffer, I plus plus. And UART is readable. UART 0. If UART is readable and I less than size of buffer, then we'll do buffer I equals UART get C. Okay, then we do that. We say wow, that's so stupid. While UART is readable. and I less than size of buffer. Buffer. Oh god. Oh, you know what? It's probably better if I do blow it up so y'all can actually read what I'm typing. Okay, so we'll do IST x bytes sent. No. Int I as a buffer. Buffer I++. Receive everything we can. Read as much data as possible. Although this is the interrupt, so realistically we just say if whatever. Read as much data as possible. Then we do auto send equals x stream buffer send from ISR, and that'll be our LiDAR buffer, and we're gonna do, that'll be buffer I and x higher priority task. Okay. If sent, well, realistically, if we stall out, it's probably bad. Well, task yield. Port. Whatever task yield from ISR is defined. Anyway, so it's possible submit to stream buffer. Okay, whatever. Batch data if possible. All right, so we do that. Then the LiDAR task is actually just receive. So we do we'll do uint8 underscore t. UC receive. Well, we said the little buffers, right, are. So what we'll do here is we're going to synchronize with LiDAR. All right, and that will do. So we do while. Or sorry, while true. I'm going to do uint8. Okay. You know what? We're just going to lift the checksum code out of my old program here. Let's do that. LiDAR checksum. Alrighty. I think it needs to be a uint32, right? No, it's a 16-bit checksum, right? Yeah. I don't know. We'll leave it as is, just in case. So then we do synchronize LiDAR. Actually, we're going to do auto decode LiDAR. Shit. What do we want to do? How do we want to do this? Need to synchronize with the LiDAR. Basically, we're looking for that FA byte at the very beginning, and then trying to decode a packet from that. So we need a unit underscore t buffer 22 bytes, because that's how each little packet is 22 bytes, right? So it always starts at 0xFA, right? So we need to synchronize. So we do want X receive. We do X stream buffer receive. LiDAR buffer. We'll do, buffer will always receive 1 byte, and then port max delay. We'll just do while true here. All right. Stream buffer receive. If buffer 0 not equal to FA, then continue. Find start byte. Find the start byte of 0xFA. Receive the rest of the packet. Receive and decode the attempt to decode the rest as a packet. So we'll do X stream buffer receive LiDAR buffer +1 21 port max delay. And we do if making me sleepy. Yeah, no, I feel that Danish. Alright, so we do if actually, yeah. You know what? Let's go just look at my old Nito code here. Read packet buffer, so we do unsigned int checksum equals buffer 20 plus buffer 21 shifted up 8. If checksum equals Nito or LiDAR checksum buffer, then break. Otherwise, we continue. Printf LiDAR synchronized. Receive LiDAR buffer size of buffer. All right, LiDAR synchronized. Perfect. So then now we can flip on our thing and check if we get anything from the LiDAR. Well, shoot. Looks like we didn't get anything. Doesn't look like the UART interrupt is being called. Well, that's unfortunate. Why is that? What does an IRQ handler look like? Void, it's just a void function. Okay. So why is this not working? Add shared handler? Oh, Jesus Christ, what the hell am I hitting? Let's see if that works any better. Oh, 0. Oh, num is UART 0 IRQ. Aw. Why is this not working? Maybe I have to... Interesting. Wonder why the LiDAR is not reading data. It's never firing the IRQ. I mean, I remember reading some data out of this. I thought. But... What if I use another random pin? Maybe I have to... Maybe I always have to set up transmit receive pins? I mean, that would be stupid, but just as a quick aside. Do I have anything hooked up to 1816, 1514? I mean, I got the I2C stuff, right? Yeah. We could also delete the servo here, just to see what happens. Balancer. just to see what happens anyway. Just to see what happens. Clearly nothing. Well, that's annoying. IRQ's enabled. We've enabled RX has data. Disabled, you know, whatever. I'm gonna run this as I'll just do stupid shit like printf if, let's see, so while true, if UART is readable, UART 0, we'll say if UART 0 get C, UART 0 equal, we're just trying to detect whether anything works. Printf LiDAR packet. Just to make sure that we didn't wire something wrong. LiDAR packet. Oh, okay. So clearly something's coming in. And then just too much data comes by. V task delay, port PD MS 2 ticks. We're gonna do 10 or 100. Throttle the message to 100 times a second, or 10 times a second. Something's happening. Okay. Let it yield some time here. Okay. Okay. So it does receive stuff, it just doesn't... Okay. Okay. Yord is readable, get C. So yeah, so for receiving data, the question is why this doesn't work. Maybe it's another free RTOS shenanigans. Why doesn't this work? Maybe we have to set the LiDAR task affinity. No, I mean, this is the interrupt handler. It should run from wherever. RTOS UART. Okay, maybe. So clearly, something is working. Okay, wait a second. How is this going? How is our print going? All right. Did I do something obviously incorrect? Let me just set the handler before I do UART init. Wait, what? Source. Oh, wait. No. Wait. Hold up. Hardware. UART. Got to do that. Is that what was going wrong? That can't be it. Hey, okay, wasn't that simple. That would have been funny. Okay. Still trying to think, why would this not be working? Why would this not be working? Crud. 11 needs a dummy thing to latch the something or another's. Wish I was missing something easy, but doesn't look like it's all that easy. So I've set up a UART interrupt. It's never being called. Even though I've set an exclusive handler for UART 0 IRQ. I've initialized the UART. I've turned it on. Okay. UART or PyPico UART IRQ never being called. Maybe IRQ set enabled. Did I forget that? I mean, does that 0 IRQ? True. Maybe that's important. I mean, I imagine it would be important, but I also just didn't know whether... what does this do? Oh. I might need to... Ooh. That might have been it. That might be it. Might need to... I hope that's it. Hey, there we go. Hello, yes. Okay, perfect. Looks like it's working now. Okay. Yes! Haha! Okay. Finally. Alright. LiDAR synchronized. Perfect. That was it. I just had to call in another enable IRQ function. So you have to enable the UART, or the mask is not set by default. Okay. There should be a LiDAR synchronized call here somewhere. Well, it wasn't happy because it printed on a different thread. What if we pin the LiDAR thread to core 0? That'll fix our print problem. There we go, LiDAR synchronized. Yeah, so looks like semi-hosting. If we call printf from not core 0, it'll blow up in our face. That's what this set affinity. It's a bit mask, so setting 1 means bit 0 set, meaning it'll only run on core 0. All right, so that's how that works. We don't need that. We've confirmed that that works. Okay. Okay, cool. We'll just rearrange this a little bit to be more clear. Set function, init, set the interrupts, and the IRQs enabled. Perfect. Okay. We're gonna say LiDAR task, tilt suite task. We'll say this is void setup LiDAR. And we'll cut all this shit into... into our setup LiDAR. Start UART 0. All right, and we're gonna cut this function into a static function, or well, a lambda here, static lambda, or a non-capturing lambda. Yeah, I wonder if there's a way to do this with DMA at some point. I mean, there is definitely. It's just you need to make it a little cleaner. Some forgive. We'll do that. LiDAR buffer. Let's go unscrew over our motors. Let's re-enable the servo. Okay, cool. We've got our LiDAR synchronized, and we validated the checksum, which means we're definitely getting data out of the LiDAR. All right. So I got synchronized, and then now each packet is definitely a... each packet is now definitely a valid LiDAR packet from the Nito LiDAR. So we can close that, close that, close that, close that. Okay, now we can get into processing the... Okay, well now what we're going to do is set up... Let's set LiDAR speed. Now let's set up the P controller to control... So right now we're just setting a speed for the LiDAR's motor, and we're not doing any sort of PWM on the LiDAR drive based on the speed data that we get. So we're actually going to come back up here and come back up here. Set up a LiDAR checksum, LiDAR task, sweep task. We're going to move this stuff up above the setup functions. Main task. All right, so what we're gonna do now that we've got this, all of this stuff, is that, wow, oh, we got this stuff, LiDAR synchronized. We're going to print out the RPM from the LiDAR packet, just to verify. Extreme buffer receive. You know what we're gonna do? We're gonna define a void LiDAR synchronize, just in case we ever need to resync. So we're going to say this is going to give ourselves a uint 8 buffer. 22. While true. This will be a return. Or break, whatever. All right. When true, receive. Right, buffer. Okay, we synchronize. In case we ever desync, right? All right, so extreme buffer receive. If receive LiDAR packet. If, all right, so we got unsigned int checksum equals buffer 20 plus buffer 21 shifted 8. If checksum not equal LiDAR checksum buffer, then we've LiDAR desync, and then we'll call LiDAR synchronize and continue. And then we'll print out the RPM. Print LiDAR RPM. Okay. Print the LiDAR RPM. So hopefully everybody understands what we're doing with the LiDAR here. We've got this checksum function, which computes the checksum based on... This is a port of this function into C. We then... yeah, how old is this post? 5 years at least. Okay, I mean... it's older than that, I know. It's not older than that. Interesting. I wrote that Nito code years and years and years and years ago. So yeah, here, yeah, so this is a port of this function into C. We're then always looking for the start byte of 0xFA. We then receive the rest of the 22, the next 21 bytes to form a packet of 22 bytes. We then verify the checksum. If it fails, we probably weren't synchronized, so we then start looking for the start byte again until we basically decode a valid packet. And then... so we try to receive a whole buffer, 22 bytes, and then if we fail the checksum, we've desynced, we resynchronize, and then now we're going to just try to read the RPM, which is the next 2 bytes. So we're going to say unsigned int RPM equals buffer 2 plus buffer 3 shifted 8. We're going to say printf LiDAR RPM percent U N RPM. Okay. LiDAR desync. Uh-oh. What? What? How? Did I screw up on copying this checksum function? Next time it tries to read, it's a desync. That doesn't sound right. I'll be honest. That doesn't sound right. I don't believe that. I don't believe that at all. Eyes of buffer. believe that. Why would it be losing so much? I don't believe it. I really don't. Again, I don't believe that I must have goofed something. I must have goofed something, I don't believe. I don't believe that it's immediately desyncing. Yeah, because read break. Read 1 byte offset packet. What is that 1 byte offset packet? Wait for the last packet to be F9. Last packet. Something. Wait. Start is always FA. Index byte. Speed is a 2 byte. Information, little endian. Data 3. Hold up. Did I do something wrong? Hold on. I get a 22 byte packet from the LiDAR. Oh, that's just to undo. It's just to not read in 22 byte increments. So you'll okay. That are synchronized. FA. Warning desync. Get the RPM, shifted 6. Aww. Something seems really wrong. Okay, for n equals 21. Try that. We're just throwing stuff at the wall. Hoping that it works. Wait, it looks like it's working now. The heck? All right. If checksum. All right, let's try that. See what happens. Link fail. So the LiDAR synchronized, which is good. And then everything fails. New checks on 1580. Ugh, what the hell? Why does it keep desyncing? There we go. Interesting. Okay. What the heck? So LiDAR sinks and then blows up. Why, though? Why would it not work? So it synchronizes perfectly happy, and then something really, really breaks. I don't know why. Why would it break? Something is amiss. I don't know what it is. What could it be? What could it be? Yeah, I'm being very quiet and just poking at shit here. What is futzing with? Why is it breaking? Why is this breaking? This might actually be wrong on the checksum function for all I know. Let's see. Maybe it's buffer. One. Yeah, no, it's not working. It's all over the friggin' place. It is clearly desyncing. I don't know why. Hopefully it has nothing to do with the debug system here. Trying to read data on me here. CMake lists or UART. I mean, disable UART, disable USB. I don't think anybody else is eating my UART, right? So why am I losing data? Why am I losing data? That is really weird. Something funky is happening here. Maybe this is getting called when UART's not readable occasionally. So we'll say if UART. If UART is readable, UART 0, then hold on. Or we go and do all that. UART is readable, UART 0, then uint 8_t byte equals UART get C. UART 0. We got extreme buffer send from ISR. LiDAR buffer, a buffer, oh no, wait. Handed to B, 1, handed to X, higher priority task. Okay. Alright. Let's do it that way. Do one at a time. See if that helps. Does not look like it helped. Oh, why? LiDAR RPM 243. What the? Still not sure if I'm doing something wrong. Like, it syncs, and then everything goes to shit, and I don't know why. Why does everything blow up after that point? Like, it feels like something legitimately is funky on the pico, you know? It's 18 minutes still. What would it be? What would it be? I do at least want to see the RPM. That'd be fun. it's funny that... What's funny is that it Interesting. I just don't know. I wonder if something to do with the affinity set? I don't know. Maybe it has something to do with the semi-hosting? That would be interesting. It could have something to do with the semi-hosting. Because that'll futz with all of the interrupts. And we're not running DMA, so... maybe what we do... Yeah, maybe what we do is... how about we go in and we disable semi-hosting completely? See what happens. So we won't get any printfs anymore, but... that happens, though. I wonder. I don't know. This is not great. Let's see. Pi Pico. You are dropping bytes. I wonder if maybe the FIFO's not quite working. That would be interesting. So LiDAR, maybe it has to be enabled, right? I mean, why wouldn't it? Just don't know. Q. Highest priority. Maybe some of the interrupts are going to the other core. Alright, something is really funky. I mean, we are getting some data in, which is good, but clearly something is not right. Clearly something is not working correctly. I doubt it's this. Like, we wouldn't get anything if that was wrong. Exactly. Client CMake, yeah. Like, we wouldn't get anything if we got the baud rate wrong. Yeah, exactly. Okay. I figured. Definitely fit 115.2k baud. But why are we dropping random bytes? The funny thing is that it seems to work well, you know, at the very first thing that we do, and then we start spinning up a bunch of threads, and then it dies. Oh, now it's happier. That's probably not the... Yeah, okay. What the hell? Yeah, something's fucky. Let me disable tilt sweep task just for now, anyway. This can't be it. We would get real bad things if we blew the stack. I'm really at a loss right now. What the hell? If we don't do the affinity set, you know? And we plunk a breakpoint there. Yeah. There's no actual work to do, so. Oh, look at that. Something's happening. Not overloading core. Not overloading the core. That's funny. Didn't we say it's 2 kilobytes deep? Trigger level bytes. What is... Oh, wait a second. Hold on. What happens if I do a stream buffer with no trigger level bytes? Stream buffer create. Trigger level bytes. Number of bytes must be before the task is blocked on the... Oh, trigger level 1 being used. It's not valid to specify a trigger level is. Before a task that is blocked on the stream buffer to... Huh, 22 we could do. Huh. So removing the affinity set seems to have fixed it? What? That's odd. Okay. Interesting. Interesting. Well, let's get a little further along here. So let's go in here and define, so packet, state packet. Let's do this. Let's define a struct LiDAR packet, or LiDAR packet. That's going to be a, that's going to have a, oh dear. We need to... So synchronize will... We got, synchronize, and then we need to, void, LiDAR synchronize. Okay, break, and so now we need to align to packet 0. Or, packet 0. So now what we'll do is... Actually, we'll do this. Void LiDAR align. While true, we do... receive LiDAR packet. Okay, fine, whatever. Find base. Find first scan packet. Do extreme buffer receive LiDAR buffer 22 port max delay. Actually, you know what we can do here? Let's do void LiDAR get packet. I'm gonna do uint 8 underscore t buffer, and this is gonna be a bool. We do extreme buffer receive. LiDAR buffer, buffer 22, port max delay. Or auto ret. If ret not equals 22 or checksum not equal LiDAR checksum buffer. Then we got return false. Return true. And checksum is equal to that. Okay. Okay. We got if not LiDAR get packet buffer. All right. If not LiDAR get packet buffer. I got LiDAR synchronize. Continue. Check. Keep going if this isn't first. Whatever. Find first packet. Find first scan packet, and that will be the second byte. And the packet's going from A0. So we got if, well, so actually what we want is F9, because then the next one will be A0. So that's what we were doing in my code, actually. Wait for the packet to be F9. If buffer 1 equals 0x F9, return. All right, I got LiDAR synchronize, LiDAR align. Okay, so the way we can test this is check if we fail out. Yeah, what? What the hell? What broke? What? What broke? Come on, man. Problems. Oh, did I? Positional PID. Oh. Oh. I broke it. Okay. Cool. There we go. That's such a non-straightforward error here. Okay. And we're not doing the thing. Yeah. Oh. Running for a while. Oh, we desynced. That's fine. Desynced. I guess that's fine. I guess that's fine. Interesting. Okay. Well, booger. Thought we were going to get this LiDAR working before the print finished. All right. So buffer one. Something is not good. I don't know if it's hardware. Okay. Well, let me. Okay. So now that we've got the thing printed, let's stop doing this for a second and switch over to mounting the just dealing with that thing. Okay. Oh, additional security. Let's see if everything lines up in the way that we wanted. Okay, well, we'll turn that off. And then, before I pull away, let me, droid cam. All right. Kitty, kitty. All right. There we go. Kitty. Hey there, Sheba. Let's see if this mounts the way that we want it to. LiDAR won't quite go the way that we plan here. Let me switch this back to my desk cam. Need to unplug the LiDAR so we can see if this all sits the way we want it to. Alrighty. Let's see if everything lines up. Probably doesn't. Probably does. Like, okay, that worked, more or less. So the camera fits. The camera does in fact fit where we wanted it to go. the holes mostly seem to, the holes seem to line up on the frame. Oh, that's not the right hole. Okay, the frame holes line up. The Raspberry Pi ones also line up. Okay, hold on, desk cam. Basically, just the LiDAR is the only question here. So we've got these holes line up. All of these line up. The Raspberry Pi lines up. See, we can see the Pi. That one. Yep. Pi lines up. These line up. And let me switch back to taking the stuff out of the LiDAR and see if the LiDAR lines up. Taking the stuff out of the LiDAR. Take these posts back off the LiDAR. And hope that the LiDAR isn't damaged or something. I doubt it. I highly suspect that this is just a free RTOS and Pi Pico interaction shenanigans. Okay. Got those. We got these. Almost there. All right. Moment of truth. Does the LiDAR fit on the mount that we made for it? The answer is looks like it, actually. The answer is it actually looks like it freaking does. Let me see if I can turn on the there we go. If we look and we see the bottoms of the posts, I think this actually lines up. Oh my. Perfect. Then with this lining up, yeah, there we go. We've got, and then there's that. The camera will chill right under the LiDAR. The Pi is mostly out of the way. I don't think a case between the Pi would interfere with the LiDAR. Because if I look over the LiDAR straight down, I see the edge of the Pi. Or I see a gap between it and the Pi. So yeah, I think we modeled this component correctly. Perfect. Okay, let's go over to the table and put the heat set inserts into this so that we can actually mount it to the robot. All right. Let's start with the M3. So we're going to do these ones first. Up, we'll put it at 450 degrees. We're also going to need our M2. These are the M2. Well, these are, well, actually we'll need both our M2 and our M2.5s. These are the M2.5, I believe. These are the M2s. Tiny little things, aren't they? Okay. Of course it got a lot hotter than it was supposed to. decontamination in the nozzle that came out. That's funny, because that means that was jammed up in there for more than the last. I mean, that means the last print went without it getting ejected from the nozzle, which is insane. Really, this is kind of an illustration of the dangers of single nozzle printers. Because even though we flushed and did everything, oh god. Oh, ew. Hold on, I need to put this down. Hold on. I apologize for the thing pointed at the ground, but I just about burned myself, so just give me a quick moment. It is late and I'm very quiet. It's not great streaming, I say. Here we go. Here. I need to put this on again because I gotta hold it. Ow. Apologies. Alright, one last one for the mounting hardware. Alright, there's that one. That one. Oh dear, hold on, that one needs to go a little more. Okay. Is that alright? So we got the 4 for the chassis mount in, we've got the 4 for the LiDAR in, so that's it for the M3s. Now we need to do the M2s. Turn the light off here. Yeah, now we need to do the M2s that hold the Raspberry Pi. M2.5s, sorry, that hold the Raspberry Pi. Actually, you know what? Hold on. I'm gonna take my phone out of the case here. Whoops. Wow. Alright, killed the camera. So we got settings. That looks awful, but hey. Gives you all a view of what I'm actually doing. Plug in the light. There we go. All right. Put these. Oops, too many. All right. So these go here. And these are the M2.5 inserts for the Raspberry Pi. thing to do is the M2 inserts for the camera. Which we'll do through the front. Just do these one at a time. Right. Alrighty, so start with that one. Okay. Wow, these are boundary. This one's a little difficult to work with. It's fine. There we go. Okay. Little tricky there. Hopefully I didn't try to put one of these in backwards. I mean, that'd be fine, it's just funny. Okay. All four of those are in. Generally flush, we can put the camera in through the back. Some of this garbage off in here. Clean the tip. There we go. Okay. Alright, so now I need to bring the robot over here and take some things apart so we can assemble it. Okay, Pi, LiDAR, camera, wrenches, we won't actually put the Pi in right now just because I don't have an SD card set up for it, and once I install the Pi, it's about impossible to get the SD card back out of it. So, all right, wrenches, robot, there we go. On back over. Okie doke. One of the things I'm curious about is if this included camera cable is long enough. It might be just long enough. All right. So let's, where's my, these are my M2 screws? Yeah, these are my M2 by 6 mil. Okay. So start with this. Oops, too many. There we go. Hey, kitties. No eating my wires. No, get down. No. Well, actually, I guess they're eating the tag on the wire, but no. No, get down. I know. You like playing with that. Alright. Okay, cool. I'm gonna put at least one of these in. unscrewed all the way down. We'll double check that it's long enough. So it needs to be long enough to get into the, oh god, do we have to flip it? Oh no, that's annoying. Okay, well that's a pain in the butt. We gotta flip the cable around before it'll actually go in because reasons. If we put the pie on the other way, it would be the right way around, but no. I didn't want to connect the cables that way. That's fine. We just have to do the old twist. Old camera cable twist. The question is whether that'll be enough room around whatever case I end up using. Let's see if I have a longer one of these cables. I don't remember which lengths I bought. I might have bought a 30 millimeter, but I can't recall. These all might be 20s. Oh no, these are 300s. These are 30 centimeter. Okay, cool. I do have a 30 centimeter cable. Perfect. All right, well, we do have a 30 centimeter. I am hesitant to use one that I don't need. But in this case, I think I actually bought it because of this robot, so it's fine. Take the camera out. I'll plug that. Plug this one in. There we go. All right. Pull that out of the way. And then one final one on the top. All right, we got the camera mounted. And yeah, there we go. Camera's mounted. Perfect. All right. So next we need to unscrew the battery mount because we gotta get under it to put in some of the bolts. So we'll disconnect the battery. And we will unscrew the mount. So that's out. Flip this over. Need to get some M3 screws, such as these. this, cable it through it, turn this over. Oh, actually, this is the more complicated one. I totally forgot. Okay, we actually have to take off the motor deck. Okay, this is the complicated one. Sorry. Let me unplug the PiPico just so I don't have to deal with these connectors. Okay. Right, we have to take off the motor deck, which means we kind of just have to take off the wheels too, so we can access the bolts. So let's do that. Which wrench do I need? I think it's this one. Nope, it's the smaller one. I should have trusted my gut because I was looking at the smaller one first. Okie dokie. Jeez. I'll put these set screws in here, something fierce. Okay, there we go. Alright, take the wheels off. And now we can take these locking washers off. Alright. Okay. Nope. Spacers. Take the other side off just to be safe. Trying to make it better and make it worse in the process. What else? Okay, deck. Where did the nut go before the cats eat it? Hey, no, give that back. Give that back. Got it. Saved it. Alright, now we've got the motor deck off. You know, might actually. There's probably an interesting opportunity to look at how these wires lay out and how the MPU is doing. Alright, looks fine. 4 and 4. Alright. Now we can put this up in here. So we'll get our M3 bolts, screws, whatever you call them, whatever you would like to call them. And we'll put this one in. There we go. Alright, got that one in. We got this one in. Alright. Probably the first time bolts have ever been mounted. in here. Just again, this chassis is one I've had but not really done anything with for a very long time. Before 3D printing, I used a boatload of double-sided tape. Alright, one to go. One to go. There we go. Sorry, interesting. I'm wanting to rotate because it's almost stripped. What the fuck? Alright, build that one out a little too much. Oh, I can fix that later. But, alright, looks like we have all of these in, which is good. And we can remount the motor deck. Let's validate that the kittens can you not eat the wires. Be real swell if you didn't. Okay, here. Just double check that these are as tight as they can be, because getting in here is kind of a pain. Alright, cool. Make sure we're not pinching any wires. Make sure we're not pinching anything. Good, we're not pinching. Let's put a couple of these back through. Let's get these on enough to have I ever told you how much I hate these kinds of nuts? And locking nuts, I really hate them. But I recognize their utility. In fact, some of my other robots here use locking washers because it's great when vibrations don't cause them to back out. And last one. Perfect. Okay. Good. Locking washers are secured, or at least they are screwed down. Okay, we got one. Yeah, no pinched wires. Pinched wires, no, just about to be destroyed. fun stuff. All right, cool. Cool. All right, let's screw the other ones down. All right. One last one over here. Ready to go. As these have tightened, some of the other ones have loosened up, so we gotta go double check all of the others. Make sure they're still tight. That one is, and that one is as well. Good. All right. Now we can put the wheels back on. Yeah, spacer, wheel. Fuck. All right. Alrighty. So we've got, so we got that in, which is good. Alright, so that's back in. No pinched wires. I hope. Looks like no pinched wires. Well, it's going to be really hard to tell either way. Those are reattached. They're not sliding off. Okay, we've got the top part mounted. Orange is a pretty nice accent color. The blue is a really nice accent color to the orange. Okay. Now what? Okay. Remount the battery. Mount. Hey, no, kitten, get off. Down, 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 all the way, all the way. There you go. All right. All right. Oh, great. Guess what can't be accessed? Oh, I forgot to put in accesses for the battery mount. Oh. Okay. Well, that's annoying. You know what? We're fucking not dealing with this shit right now. Okay. Hit him. What are you doing? Okay, what we're gonna do is called destructive modding. I don't want to deal with this. I don't want to reprint this. I'm gonna take my Dremel and punch like 2 holes through there. Okay. Okay. Dremel bit. Is that will hit the metal? Good. Do that. Get that. access ways that we need. All right, cool. Okay. It's hot because it hit the metal. Okay. There we go. We've drilled 2 access holes. That won't get us all the way through because we need to access all the way down. So we need to be able to hit the we don't want to hit the. Okay, I have longer M3 screws, so we'll just use those instead of the countersunk ones for now. Just so we don't hurt the thing. Okay. So, given this new information, alright, well, whatever. So we're going to put these in here. Screw through the top. How far will those go down? Long enough. All right. Far enough. Perfect. And right. Here, hold on. Make sure I get this. There we go. Oh, shoot. I'm collapsing the print. Anywho. Alright, so now for the countersunk. Honestly, these can just back off. For now, countersunk one's in. Alright, now we'll tighten these ones up. Alright, cool. We'll go into the 3D model and fix that at some point. But yeah, so we got that. Let's grab the LiDAR, put LiDAR bits down in there. We'll grab some M3 bolts, not those, these. Or these. 3, 4. Hope these are, the heads are not too wide. is mounted, and it's got some clearance in the camera, and life is good on that. All right, we'll go into the 3D model and unscrew up the model for the unscrew up the model for the or make sure to put the access routes in for the stuff, right, for the countersunk bolts. Make sure to get any metal shavings in here. Aim. All right. Put that in there. And then put that one in there. There, all right. Put the debug cable through there, through somewhere. There we go. Should try to figure out what the heck happening with our UART. We'll figure it out. All right, the LiDAR is attached. We're going to be able to route something. Our cable for the Pi just to test this whole thing out right now, or conceptually anyway. I seriously burned myself on that drill bit. That's annoying. Annoying. Alright, well, let's figure out what to do with this. How to properly route that around to make it do what we want. I mean, realistically, all we gotta do is route it into there, but we gotta figure out how to make it not show up in the LiDAR's view. And that's our debug cable. And let's at least put the bolts into the Pico here, just so we can. Do I have any short M2? I thought I did. I had some 6 mils somewhere here. There we go. Yeah. 6 mil screws. Alright. We'll just put 2 of them in for now, just because I'm going to have to take this back apart later, put an SD card in it. Ow, sorry. All right, cool. Got that. We got that. And now what we're going to do is route the USB cable that'll power the whole thing. Yeah, so none of that's in there. Come in, we can plug Pico. Move this around. Make sure we don't pinch anything. Oh, okay. Well, that's a critical failure. It's not tall enough. Well, I'm gonna have to make some spaces for the pie because of that. Damn. Right in the last step, I didn't even think about that. Hey, the angled piece that connects the pie. Oh, it's not tall enough. Damn. Okay. Well, we'll have to fix that at a later time. That's annoying. Shoot. Actually, you know what? Just so we can test this out today, I think I have a few little homemade spacers that we can use to prop up the pie. Yeah, I got a couple little spacers I made. We'll use not those, a little bit for. There we go. Those ones. Okay. Sorry that I'm being real quiet at the moment. I'm just heavy. My thoughts are heavy. Okay. There we go. There we go. That spacer in. No. Come back. There we go. There we go. Cool. Gotcha. Nice. Okie doke. Now we should be able to plug this thing in. Yeah, there we go. All right. And so if we do our good old little tilt here, a little twist. Twist. Cable. Oh god, that's horrible. And sorry for the bump. Just getting late, getting tired. Go. All right, cool. Just try to. Oh no. Don't get hung up in the heatsink. No. Okay. Okay. Well, good enough for now. Okay. So. Okay. Now let's plug the battery in. Not drop it on the LiDAR. Fish this connector up here. Alrighty, that's connected. connected. So now we flip this switch. Hopefully no smoke. Hey, there we go. And we have a green power light on the Pi. I think you can see it. There we go. All right, yep, and the fan's spinning on the Pi, which means that it's sort of happy, at least. Just running an internal test code. All right, LiDAR spins, the robot's intact. The Pi didn't evaporate. And I might print another one of those. Let me grab another one of those spacers. Yeah, okay. Yeah, it's a little noisy with everything spinning here, but there we go. We've got Gen 1 hardware, or first hardware iteration together. All right, and it's buttoned down, and I mean there are some cables exposed, but we'll fix that here in a bit, or well, in the future anyway. Alrighty. So I think this is good on the hardware for now. We now have a robot that we can sort of start working on ROS with. Or working with ROS with. Yeah. Actually, let me get a little back closer to my microphone here, I guess, because I am a little further away. Oh, hi. Hey, Ryan. Hey, Jib. Why, hello there. Why am I still up late? Okay, so I think that's where I'm going to leave things for tonight. So yeah, we've got the whole thing put back together. We've got the LiDAR running. I'm going to try to figure out what the heck was going on with the UART. See if I can get it sending data correctly. Yeah, so... Oh, geez, over 6 hours. Okay, so that's where I'm going to leave things for tonight. And thanks for watching.